No. ना मु स्टार्ट करिवि से गुटिका अछि ओके आपण करा काम करी
Hello sir, good morning.
आपण सर हे गेला बर्तन आसीन आपण जागा बुकिंग हो जाए
कामू जॉइन कर देलानी ए रिसर्च ना और जॉइन को हां तो से ये की क्या चैट को मैं आई
अराउंड 27
रिसर्च पर्सन जने
और ना करते
हैं आ जन का ना है मानस रंगन या
सबमिट कर देली बर्तन जहां कहिबे सब सुनिबो सो यू कैन डू दैट
से आसीओ स्क्रीन केमिति तर रिसर्च पर्सन सेटा मार देले पळे आसीबे तो
अब स्टार्ट करन लगे मैं कर दे स्टार्ट
एटी चेक से 8 को ना कोन हां 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 अच्छा एपटे गेन देवा छागा तो हां
अच्छी उठे
अच्छी ओके बहुत चलो तो नमस्कार
A very good morning to all. Today we all are gathered here for a national webinar on the topic Advanced Two-Dimensional Materials for Energy Applications, organized by Department of Physics, Pattamundai College, Pattamundai. I am Deepika Ranidash, final year student of this department, acting as the coordinator for this webinar. Pattamundai College, Pattamundai is a premier institution of Kendrapada district in state of Odisha. This institution is celebrating Golden Jubilee of the year. This institution has earned a lot of name and fame in social as well as academic fields, as has created so many scholars which are now well placed in different fields and providing their services in and out of the country. Today, I'm very delighted to get this opportunity as the coordinator. First of all, I convey my best regards to the chairperson, Professor Adhikari Lakshminarayan Das, principal of this college, respected resource persons, Dr. Chandrasekhar Rao, Associate Professor, Jain University, Bangalore, Dr. Manas Ranjan Parida, Laser Engineer, MSOT, Oxford, United Kingdom. Our beloved HOD Dr. Ramesh Kumar Sahu Sir, co-convener of this webinar, respected learned participants, and my dear friends. I would like to request Mr. Vaikunta Charan Rao Sir, co-convener of this webinar, to give a brief introduction of resource persons, Professor Chandrasekhar Rao Sir and Dr. Manas Ranjan Parida Sir, for the technical session.
Professor Vapour Charan Rao.
Sir, good morning. Sir, on mute. You have to unmute. Not audible. It's not audible. Maybe you have to unmute. It is muted. Sir, it is muted. It is not audible. It's muted, sir.
Am I audible now, sir?
Yeah, it is audible now.
Yes, yes.
Saradiya Abhinandan. Very nice morning to all the learned participants joining in this webinar from our college and other colleges of the state. Respected IQAC members, alumni, dear students. I have the honor and privilege to introduce the guests and resource persons of the webinar. First of all, I convey my regards and gratitude to all my teachers and seniors joining in this webinar. Now, I would like to introduce the chairperson of this webinar, Professor Adhikari Lakshminarayan Das, Principal of PATTAMUNDAI College, PATTAMUNDAI. Esteemed sir, your cooperation and motivation leads us to organize this webinar and other developmental activities of this institution. We are always obliged for your commitment for the betterment of the institution. Next, I would like to introduce the convener of the webinar, Dr. Ramesh Kumar Sahu, head of the department. He has all sincere effort to make this webinar a successful one. He is an ideal teacher, a loving personality. I convey my best regards to him. Next, I would like to introduce the resource persons of the webinar. Success is a journey and not a destination. PATTAMUNDAI College, as well as Department of Physics, feel proud to introduce both the jewels of this institution. I think our students get inspired from your successful journey. First of all, I introduce the keynote speaker for the first technical session of this webinar, Dr. Chandrasekhar Rao. He is now working as Associate Professor at Center for Nano and Material Science, Jain University, Bangalore. He is an alumnus of this institution, having excellent academic achievements. He is a DST Ramanujan Fellow at IIT Bhubaneswar, completed his PhD from Jawaharlal Nehru Center for Advanced Scientific Research under the supervision of Bharat Ratna Professor C.N.R. Rao. He did his postdoctoral research at different universities abroad, like Singapore, USA, South Korea. More than 100 research papers of him have been published in international journals, and he edited 2 books. He is the associate editors of journals Royal Society of Chemistry and other internal journals USA, and awarded many prestigious awards as a scientist. You are most welcome, sir. Next, the keynote speaker for second technical session is Dr. Manas Ranjan Parida. He is also an alumnus of this institution. He completed his PhD in physics at IIT Madras, Chennai. He is a laser engineer. Now he is working in Oxford, UK at AIMSolve, which is a photovoltaic-based company. He was a postdoctoral fellow from 2014 to 17 at Kaust Solar Center. He was working at Argonne National Lab, USA from 2017 to January 2020 as research collaborator. He has studied for the development of the next generation of solar cells, photodetectors, visible light communication on perovskite and other low-dimensional materials. He has also more than 35 publications have been published in peer international journals. Heartily congratulations, both of you, sir, for your consent for this webinar as resource person. Again, I heartily congratulate both the participants.
ଲାଇବ୍ରେରୀର ନମ୍ବରଟା ମୁଁ ପାଇଛି ମାନବ ସେ ଆଉ ଚାରଟା ନମ୍ବରଟା କି
Thank you
ଆଉ ତିନଟା
all.
ଆଉ ତିନଟା କି
This is from my side.
ଯେହେତୁ ଆମେ ଆଡଭାନ୍ସ ପେମେଣ୍ଟ କରିଥିଲେ ସେ ମାସ ସେଟା ରହିଲା ହଁ
Now I would like to request Dr. Ramesh Kumar Sahu, sir, convener of the webinar, to deliver his welcome address.
Am I audible? Hello.
Yes, sir. Yes, sir.
Good morning to all participants. Esteemed principal, honorable guests and resource persons, teachers of our college and other college, and my dear students. It is a great pleasure to me to give the welcome address to the honorable guests of the national webinar as convener of the webinar meeting. At first, I welcome to our esteemed principal, Professor Adhikari Lakshminarayan Das, who has encouraged and motivated us to organize the today's seminar and make it grand success. I welcome to our resource persons, Professor Chandrasekhar Rao, Associate Professor, Jain University, Bangalore, and Manas Ranjan Parida, Leisure Engineer, who are young scientists. I welcome both of them to the today's seminar. I welcome to the teachers of our college and other colleges who are joined to us to make the webinar success. I welcome to my dear students who have joined in the webinar to gather some knowledge about the webinar of topic Advanced Two-Dimensional Material for Energy Applications. Before concluding my speech, I give a brief introduction regarding the topic, the two-dimensional advanced two-dimensional material for energy applications. Energy crisis is a global problem, and many scientists working research for development of new technology to solve this problem. Our topic is based on the synthesis of two-dimensional material and how it is used in making supercapacitor and solar cell for storage of energy, which is very interesting topic in the present scenario. Now, I conclude my speech, and once again, I welcome all the participants who joined in today's seminar, and I request all cooperators to avoid any unwanted technical problem. Thank you all, and
Thank you, sir. Now, I would like to request our esteemed principal, Professor Adhikari Lakshmi Narayan Das, to deliver a brief address to the participants as well as the guests.
A very good morning to all of you, those who are joined with us in this national webinar. I welcome all the delegates, all the participants, all the resource persons and other dignitaries who are with us on today's webinar, organizing by the physics department. As Dr. Saul told now, that this two-dimensional materials for energy application is a very interesting subject for the students of this college, and the students who are joined with us of different colleges of the district. Really, it is proud of us. We are very fortunate enough that we have two eminent scientists joined with us in this seminar, and both of them are the alumnus of our institution. It is really a great pleasure to me that both of them has certainly reached a great height where the world will acknowledge. Again, I not only congratulate them, but also I welcome both of them to join with us and accepting our invitation to deliver a beautiful presentation today. I will be happy if these two scholars, researchers and the scientists will visit their alma mater if they have time after this COVID, and they will interact with our students lively. Then it will be no doubt better for it will be benefited to them. The students will see that this college has produced such type of students, those who are son of soil and now established in different parts of the country and outside of the country. So I will not take much more time because these two resource persons will deliver at least 1 hour to our students. It is really a beneficial topic for our participants, to our students. Once again, I welcome all the participants, teachers, students, and above all, these two resource persons of this webinar today. Thank you all. Thank you all.
Thank you.
Thank you, sir.
Now, I would like to request, first of all, thank you to our principal, sir. Now, I would like to request Professor Chandrasekhar Raut, sir, to deliver his thoughts.
Very good morning, all. So it is my pleasure to get invited from my college, Patamundai College, where I did my up to my BSc plus 2 and BSc I studied there. So it is my pleasure to deliver a talk like webinar here. So I thank my sir Ramesh sir for giving me this opportunity to deliver this talk on this research topic which I am working now. And also I thank this co-convener Dr. B.C. Raul for his effort and invitation. And I thank Professor Adhikari Lakshminarayan Das, principal of this Patamundai College, for the nice introduction and the invitation to visit Patamundai College. So I will definitely visit the college after this COVID, and I will try to interact with the students and encourage them for research and different to get to know about the different research activities which we have in, like they can pursue. So I had visited once Patamundai College maybe 2 years back when I was in Bhubaneswar. So I'll definitely visit again. So thank you, sir, for the invitation. So today I'll be talking some of my research activities which we are doing now. I will try to go very simple because I don't know, most of these participants are maybe students, so they may not follow what we are doing. But I will try to go very simple and maybe material aspects of these topics and basic applications in related to energy storage, like supercapacitors related research which we are doing, that I will try to cover. And my friend Manas, he will be covering solar cell photovoltaics applications of 2D materials in the next talk. So I will go very simple. I'll try to cover whatever students can follow. So I'll try to share my screen now. Then I will start my presentation. Is it visible, my screen?
Yes, sir.
Yes,
sir,
yes.
visible, sir.
Yes, visible.
Okay, so I'm from Jain University. Already, sir has introduced me. So today I'll be talking on 2D materials for supercapacitor. Supercapacitor is basically one type of energy storage devices. So if you students know, there are different types of energy storage devices. One common example is batteries. There are different types of batteries like lithium-ion battery, sodium-ion battery, aluminum battery. So nowadays people are working on different types of batteries to achieve high performance energy storage devices. So basically a supercapacitor is like one kind of energy storage devices. So their working principle is a little different than these batteries. So today I will talk something about these 2D materials, their synthesis, how to synthesize them, how to characterize them, what is 2D materials, what is nanomaterials. Then I will show some of our research on supercapacitor applications of these 2D materials. So we are located in Bangalore, in south part of this Bangalore. So it is basically our center is very new. It is around 7 years old, but they are doing very good in terms of research activities. So we are very a dedicated research center for this different material science, nanomaterials, and their applications. Something is this coming from my side? This lines. Hello.
I think so. You maybe undo or something.
Yeah, something came on. I don't know how it is.
Yeah, yes.
So maybe I'll share again. Just
okay. Yeah.
Okay.
Yeah. Now it is okay. Yeah.
Yeah. So we are located in the south part of this Bangalore. It is around 85 kilometers from this airport. And if somebody is interested, they can definitely plan to visit our center to know about the research activities which we are doing, and to get some idea about the experimental facilities and what we are doing, what is the recent trend in this kind of materials research for energy or different environment applications, and different types of things we are doing. So we have different programs, like we have a master's program in chemistry and PhD programs in nanoscience, material science, physics, and chemistry of these materials. So basically today I will be talking on these 2D materials. I'll give some brief introduction about 2D materials, nanomaterials, then graphene, then how to prepare them, this graphene and their graphene analog 2D materials, how to characterize them, what are the different applications people are working in worldwide, very emerging applications of these 2D materials, and then some of our research on 2D materials for energy storage like supercapacitor device applications. So this is our research activities of our present group, which we are doing in our this Bangalore Research Center. Basically, we work on different types of 2D materials. There's 2D materials is like materials which is very flat. So if you take atomic thickness of some material like carbon material, suppose if you take example, so one atom thick of this carbon material is called as graphene. So graphene is like, if you take carbon atoms arranged in the 2D shape, it's one atomic thick, it is called single layer graphene. So there are large number of large varieties of 2D materials. They are graphene-like materials. So they have very interesting properties due to their atomic thickness, or due to their high surface area, reactivity, chemical activities, or electron conductivity. Like this, people are seeing what are the possible applications which can give a very enhanced performance of the device if you use. So that we are trying to do some materials based on this 2D structure of materials. So what we do, we try to prepare them by different physical, chemical methods, then characterize them, whether to know this is a 2D materials, or whether it is a pure material, or there are some impurities. So there are different types of analytical tools. By using that, you can confirm whether these materials are, you got whatever you aim to prepare, you got or you achieved it or not. So if you didn't achieve, then how to again modify this experimental parameters to get the pure form. So we try to do that. Then after preparing this material and after confirming that it is a pure phase material or it is having no impurities, then we go for different types of applications depending on their properties. So we study different properties like electrical properties, optical properties, then magnetic properties, mechanical properties, like different types of properties of this material we study. Then we do different applications like field emission, different sensor application, gas sensors, biosensors, chemical sensors. We do some energy application, basically supercapacitors based on these materials we are working on. So this is some of this overview of some of our research activities which we have published in last few years. Some of this work I am showing here, and there are large varieties of 2D materials. Like if you take single layer of carbon atom, it is called graphene. But similar to graphene, there are large varieties of 2D materials. Some of them are like transition metal dichalcogenides, like if you see molybdenum disulfide MOS2, tungsten disulfide WS2, or boron nitrides, then carbon nitrides. So there are large varieties of 2D materials which is available in literature, and people are working worldwide on these materials. So due to their interesting properties, we also have worked some of these we have worked on some of these materials, and recently also our students are working on this material. So density of states. What is density of states? So I think many of the students may be knowing this, what is density of states and how this density of states vary for different types of materials. So if you take bulk materials or bulk semiconductor, the density of states like states available at particular energy or energy values, that is called density of states. So if you take 3D materials, their density of states will be, the relation will be shown in this graph, first graph in the below figure it is written. It is parabolic in nature for 3D or bulk materials if you take bulk semiconductors. But if you go on changing this structure like different nanostructures, 2D materials, 2D nanomaterials or 1D materials or 0D materials, their density of states will change. So 2D materials, like we are confining these atoms in a 2D structure, like in a sheet-like structure. So if you are confining these atoms in 2D structure, so the atom is only moving in one plane. So it is not allowed to move in all 3 dimensions. So if you do like that, so their density of states will be like this staircase type of behavior it will show. So similarly, like if you take 1D structures or 1D nanomaterials, for example, if you are taking some nanowires or nanotubes, so their density of states, it will be like this kind of sawtooth kind of behavior it will show. So that also will have different quantum mechanical phenomena or quantum mechanical properties. So by employing their different quantum mechanical phenomena or properties, people are building different types of devices, which is giving very enhanced performance compared to their bulk structure. Suppose if you take some gold bulk structure, so gold is basically yellow, all people knows. But if you make gold nanoparticles or gold nanorods or nanowires, their properties or their colors is different compared to this their bulk structure. So it can give emissions in like blue, orange, red, a different color emission it can give. So this is just one example of gold or gold nanoparticles or gold nanostructures. Similarly, for different types of materials, if you change their size to nano level, so their properties will entirely be different than this bulk properties. So by employing their nano structures or nanomorphology or nano like properties related to nanostructures, people are doing different applications of these materials. Similarly, 0D materials like zero dimension materials. The atoms are bound in 0 dimension, like they are not allowed to move in all these 3 dimension. They are confined in 0 dimension. Like if you take one dot like quantum dots. So there the atoms are only confined in 0 dimension. So why they are called, all these are nanomaterials, because their size in nanometer range. So nanometer is 10 to the power minus 9 meter. So all this size of these nanoparticles or nanowires or nanorods or nanosheets or graphene, so their size is basically nano range, either their thickness or all this diameter, or this, if you are taking 0 dimension, their particle size is in nanometer range. Like basically it should be less than 100 nanometer. 0 to 100 nanometer, if it is the size, then it is called as nanoscale particle or nanoscale materials. Okay, so this is graphene. Graphene, about what is graphene already I told. So all of you know about bulk forms of graphene or graphite. So basically, if you are taking 3D forms of carbon, it is graphite. So graphite has different structures. If you take 0 dimension nanomaterials or 1D materials or 2D materials, they are having different nanostructures. So if it is a 0 dimension of carbon, it is called fullerene. Fullerene means it is size is in 0 dimension, and these atoms are arranged in like in this ball type of structure. So then it is called fullerene or C60, carbon 60, because 60 atoms are there in this. So they are called C60. So carbon nanotube, what is carbon nanotube? If you are taking graphene or single layer or bilayer or multi-layer of carbon sheets, if you are rolled in a cylindrical manner, it is called carbon nanotube. So they can be like a single layer carbon nanotube, bilayer carbon nanotube, or double layer carbon nanotube, or multi-wall carbon nanotube, depending on their number of walls or number of sheets involved in these nanotubes. So graphene was basically discovered by Andrew Gem and Novoselav in 2004. And due to that, their discovery, they won the Nobel Prize in 2010. Okay, so what they did, they prepared this graphene sheets by a micromechanical exfoliation method. So they took a bulk graphite, like they have taken highly oriented pyrolytic graphite. It is short form is HOPG. So they took that and they used some scotch tape. So easily available scotch tape or cello tape kind of tape they have taken, and they try to remove one layer of graphite from this bulk graphite, and they transferred into a substrate. And by doing this method, they could achieve a single atomic layer of carbon. So that they termed as graphene. So it was discovered in 2004. And they studied some electrical properties of this graphene, a single layer carbon, and they fabricated a field effect transistor based on this material. So after that, people started working on different aspects of this graphene, and then it is very interesting topic, and large number of research articles are getting published every year based on this. So after this discovery, people try to explore other 2D materials, like they are graphene-like analog 2D materials. Like they already, I gave some example like transition metal dichalcogenides. So people also are working recently on this different other 2D materials, and by preparing their single layer, bi-layer, multi-layer structures, people are doing different applications of these materials, and different properties are being explored. Okay, so this already mentioned. So if you are taking a single layer graphene, if you can roll it in different orientation. Suppose if fullerene, already told about fullerene, or it is zero dimension carbon allotrope. So if you take single layer of graphene, if you roll it in the form of a ball or buckyball, it is called as, so it will form as a fullerene or zero dimensional carbon. And similarly, if you take a single layer graphene, if you roll it in cylindrical orientation, it will give a carbon nanotube. If it is a single layer graphene sheet, it can give a single wall carbon nanotube. And if it is a bi-layer or multi-layer graphene sheets, if you roll them, it can give a multi-wall carbon nanotube or double wall carbon nanotube. And that also getting large number of interest in recent years, and people are doing a lot of research activities. Actually, carbon nanotube was first discovered before this graphene was discovered. It was discovered by Ijima, one Japanese scientist who worked on this carbon nanotube synthesis. So luckily, they prepared carbon nanotubes by some research method, and after that, people started working on them. And in 2004, this graphene was discovered, and recently people are working on different other 2D materials, which is graphene analog or graphene type 2D materials. So we are also working some of these interesting materials, which are graphene analog 2D materials. Some of them I will show in my next slides. So why graphene is so important? So due to their single layer or multi-layer like 2D like structures, it is having lot of interesting properties. So if you see, they are they are highly transparent in nature. So if you are taking a single layer graphene, the transparency is 97.7%. And that if you are taking a single layer graphene sheet, the thickness is around 0.34 nanometer. So you can imagine how thin it is. Okay, and due to that, this 2D structure, their high surface area you can achieve. So people have reported surface area of 2,630 meters square per gram. So this is the surface area. People are achieving high thermal conductivity, high electron mobility, high Young's modulus. So all these are interesting properties of this graphene or single layer graphene or multi-layer graphene, you can tell. So by employing this kind of properties, people are fabricating different devices. So some of these applications are also involved in energy related applications like energy storage devices, energy storage device like lithium ion battery, sodium ion battery, then supercapacitors, and solar cells, different types of energy related application people have also worked on. So there is some drawback of graphene also. What is that? Because due to their like metallic nature, or if people tell it is having very low band gap. So this low band gap, due to that, it is very difficult to achieve many applications which is like optics related applications or optoelectronics applications or high performance field effect transistor application due to their low band gap or zero band gap nature. So all this device application is not possible by using graphene. So to avoid this or to get better performance of this 2D material, people explore other 2D materials. So some of these examples like MOS2, WS2, and molybdenum selenides, tungsten selenides, chalcogenides, nitrides, carbides. Nowadays people are working on different carbides. So they are doing research because there are wide range of 2D materials. So they are like graphene-like materials, like seeds-like materials. So by tuning their number of layers or number of like depending on these atoms, it can have different properties. Like it can be either semiconductor, metal, or insulator, or superconductor. So it can have different types of properties depending on the material which we are choosing. So due to these wide varieties of materials, people also try to put one material above the other, like they prepare heterostructures of these materials. By making these heterostructures, one can achieve like hybrid properties of these 2D materials. Suppose if you are taking one layer of graphene, you can put another material above the graphene, like MOS2. You can also put it. You can put one more material on above it. Like you can make sandwich structure of these 2D materials or heterostructures of these 2D materials. So their properties is also entirely different than this individual material, and due to their hybrid nature or enhanced or different interesting properties, people are exploring other applications of these different materials. Further, it is also possible to tune their properties. You can tune it by different approach. So all of you know there are different phases of this material depending on this atomic positions, atomic orientation of this material. So one can achieve different phase of the material. Suppose you take MOS2, molybdenum disulfide. It is a 2D materials. So there, if you tune the properties, like it has different phase, 1T phase, 2S phase, like these phases are there. So if you tune their phases, you can also make them material like metallic or semiconductor, depending on this their atomic arrangements. Defect and vacancies. If you create defects or vacancies in this material, their property is also tuned or their property also changed. So which is beneficial for some of these applications. In recent times, people are exploring that. So heterostructures, people also do heteroatom doping, interlayer engineering. What is interlayer engineering? So these are like 2D materials. So their layers are separated by some gap. It is called a van der Waals gap. So all these layers are separated by this van der Waals gap. So one can also tune this interlayer distance by different approach. So one approach is intercalation. So by this intercalation approach, people are tuning this gap between them, their property also can be tuned. So different other approaches like pore or hole engineering, making porous structures of this material, making hybrids, heterostructures, people can also tune their properties. So this is just a brief overview of different applications already people have explored for this graphene-based material. So depending on their high surface area, reactivity, or catalytic properties, people have explored different applications like hydrogen storage, field effect transistors, energy storage devices, then there are flexible electronics devices. So these are recent research activities people are working on, and similarly also other 2D materials people have tried. So this is just a brief overview of different 2D materials I gave. So if somebody is having any doubt or questions, maybe after the talk we can discuss more. I'm just giving some brief about all these aspects of different 2D materials. 1 hour is not sufficient to cover most of the topics. and also the students may not follow if I go more deep. So I'll just try to go very simple here. So how to prepare these 2D materials or graphene? So there are different types of methods. So depending on their approach, it can be classified into two. Like one is bottom-up approach, another is top-down approach. So in 2004, Novoselov and Andrew Game, they discovered graphene or single-layer graphene. They followed this top-down approach. What is top-down approach? So in if you have to take a graphite, like ball graphite, then you have to break it or break it, or by peeling it, or by using scotch tape, mechanical exfoliation method. You have to take it out like single layer or bi-layer or multi-layer graphene from this. So this is called top-down approach. Top-down means from top we are taking bulk and achieving this nano level of this material. And of another method, in the top-down method, there are many approaches like exfoliation, then unzipping of carbon nanotube, intercalation, graphite exfoliation by chemical approach. So all these are top-down approach. In bottom-up approach, so we have to prepare them by growth, atomic, from this atomic level, we have to grow this material. So by chemical methods or chemical vapor deposition method, epitaxial growth method. So these are the common methods used for this growth of this graphene by bottom-up method. So it will be growing atom by atom from this on these substrates. So these are the two types of methods, top-down and bottom-up approach. I will show some of these examples here. So this is one CVD. It is called as chemical vapor deposition method. So in this method, this belongs to bottom-up method, bottom-up approach method. In this approach, for the graphene growth, they use a tube furnace. Tube furnace, so high temperature tube furnace, which can reach 1200 to 1500 degrees centigrade. And they have arrangement for this vacuum and different gas flow arrangements. They use mass flow controllers. For the graphene growth, we have to use carbon source, like carbon gas people use like methane gas, CS4. So CS4 is the carbon source for this graphene growth. And hydrogen, argon also they use. Argon to achieve this inert atmosphere, hydrogen and CS4 methane mixture they use, and they standardize particular concentration, this graphene growth is possible. So usually people take copper or nickel foil, which acts like a catalyst to grow this graphene on this substrate. So this is the arrangement, and this instrument looks like this. So by flowing this methane gas in hydrogen argon mixture and in particular vacuum, one can achieve different graphene layers. Like it can be single layer graphene or bi-layer or multi-layer graphene. So after this is the image of this CVD system, like chemical vapor deposition setup, where this mass flow controllers and this quartz tubes are there, and this is a splitted furnace where we can set this temperature as per your requirement and then do this growth. Then this is how, once you grow this graphene on some substrate, how to transfer. So this is the transfer approach which widely used by different research groups. So once it is suppose grown on this copper foil is acting like a catalyst for the growth of this graphene. So once you grow them, so next steps involve like how to etch this copper, because copper, if it is there, it is not applicable for different device application. So you have to etch this copper from this graphene. So they do this different etching treatment and transfer of this graphene to substrate. So this just schematic I showed. This is chemical approach, or different steps are involved to transfer this graphene into a substrate. So another approach is plasma enhanced CVD approach. So it is short form, it is PECVD. So in this approach, basically plasma is generated, or plasma is created in a vacuum chamber. So this schematic of this setup and this experimental PECVD setup is shown here. And in presence of this hydrogen plasma, at particular temperatures of 400 to 600 degrees centigrade, and you have to heat this chamber in particular vacuum, and then you have to pass this gas, methane gas, CH4 is the methane gas, and CH4 argon mixture you can pass it, and by varying this temperature and time of growth, you can achieve different layers of this graphene. Basically, by this plasma enhanced CVD method, people achieve vertical structures of graphene, like they are vertically aligned. So you can see some of this scanning electron microscope images of this vertically aligned graphene. So they are grown on different substrates. Like here, catalysis is not required. Without catalysis, without catalyst like copper or nickel, one can achieve also. And sometimes people just thin film of nickel or copper, they coat on this silicon substrate to achieve better quality of graphene growth. Okay, so this is the mechanism. So maybe it is difficult to follow by all the students. So I skip this slide. So next example is silicon carbide based approach. So in this approach, people try to grow silicon carbide on some substrate, and they anneal or heat the silicon carbide in vacuum and very high temperature. It is 1400 degrees centigrade, and in hydrogen. If you are passing hydrogen and heating this, so this hydrogen will help to etch this silicon from the surface. So if you are etching the silicon, so you can achieve carbon, single layer carbon or bilayer carbon. So they also characterize by different approach, like lead. One approach is lead, and there you can see this diffraction, electron diffraction patterns. So from this electron diffraction pattern, you can confirm whether it is a graphite or single layer carbon or graphene. So from that, they confirm. Pulse laser deposition is another type of this bottom-up approach, because we are growing atom by atom of carbon or graphene layer on this substrate. So this is the schematic of a pulse laser deposition setup, in which they use different like source material. It is like, suppose you are using nickel or HOPG, like highly oriented pyrolytic graphite, as the carbon source, and nickel as the catalyst, like catalyst source, and this is the rotating target. So on this rotating target, your laser beam will fall, and this chamber is a vacuum, and when it is rotating, and depending on this laser power which you are giving to these samples or targets, so it will like plumes will be created depending on this laser power and intensity of this laser beam. So these plumes will be deposited on your substrates. You can either take silicon substrate or any other substrate which you want. On the substrate, they will get deposited. So by this approach, you can also try grow multi layers of this carbon or metal structures. Like you can first grow nickel films. On that, you can grow carbon like graphene layers, and again nickel layer, and again graphene. Like that, you can make heterostructures or multi-layered structures of this graphene. So this is one of this interesting method to grow graphene. So arc discharge. Arc discharge was first employed for this carbon nanotube growth. So by same approach, people have also tried to grow graphene. So arc discharge is like, it is having two electrodes, and it is in vacuum, and we are giving very high voltage to produce some arc. So we have some positive electrode and negative electrode. If both these electrodes come to each other, like come to very close to each other, there will be production of some arc. Arcing will be produced. So in this arcing process, if you are using carbon or carbon electrode or graphite electrode as one electrode, so during this arcing process, your carbon nanomaterials will be produced. So these carbon materials can be like carbon nanotube or graphene or carbon fullerenes. So these are possible. So depending on this experimental condition, people also have achieved a carbon nanotube growth or graphene growth by this arc discharge method. So this is the micromechanical exfoliation method. So this was the method by this Novoselov and Andrei Game first followed to achieve single layer graphene. For that, they won the Nobel Prize. So what they did, So they have taken this HOPG, like carbon source, carbon substrate. HOPG is like highly oriented pyrolytic graphite. So from this graphite, you have to take one Scotch tape. Scotch tape is easily available everywhere. So by using this Scotch tape, so you have to press it. This Scotch tape you have to take and press on this graphite surface, and by pressing, you remove that one layer or few layer of your carbon. Then you put on some substrate. So in the bottom it is shown. So you're taking a silicon dioxide, silicon substrate. On that you can press it. So you press it and again take it out your Scotch tape. So some layers of your graphite will be get deposited on this silicon oxide substrate. So that is the single layer or bilayer graphite or multi-layer. It can be multi-layer also, but depending on your how much you press it or how much force you have given when you are transferring this graphite, so you can achieve single layer also. So by this approach, they have achieved single layer graphene, for which they won the Nobel Prize in 2010. So then how to know whether it is a single layer or bilayer or multi-layer graphene? There are different types of characterization techniques. I will just briefly show some of these examples on different characterization techniques. So this is another approach. This is also called bottom-up approach. So bottom-up approach is basically this mechanical method, micromechanical approach is the bottom-up approach also. So other chemical approach is there. So in this chemical approach, they do exfoliation, ultrasonication. Ultrasonication is one approach. You take a bulk form of your graphite, then you do exfoliation in different solvents or different intercalating agents. Because this graphite is layered material, so all these layers are stacked, like stacked above one of the above. So if you are using some intercalating agent like lithium, sodium, potassium, like that, so what will happen? This lithium, sodium, or potassium, whatever you take, these are intercalating agents. So these atoms will go in between these layers. So if you put these atoms inside these layers, so they will exfoliate, and it can form few layers of this graphene sheets. So by this method, people achieve this graphene sheets in different solvents, and they make a dispersion of this material. And this is very widely used technique to prepare this graphene sheet in bulk quantity, because in micromechanical exfoliation approach, we cannot achieve bulk quantity. If you need to prepare some devices like energy storage devices, you cannot get enough materials by these other methods. So this chemical method or chemical exfoliation method is the widely used method to achieve bulk amount of materials for different applications. And this is electrochemical exfoliation. This is another approach in which they use electrochemistry, like you have cathode, anode, and then use graphite, and then graphite is exfoliated to form few layer or single layer graphene. So this is the chemical method. It is widely known as Hammer's method because Hammer first discovered this approach. This is the chemical oxidation method. They use reducing agent like potassium manganate, H2SO acid, and H2O2 to exfoliate the graphite, bulk graphite, to achieve single layer or bilayer. Single layer, it is little difficult to achieve by this method. Usually, few layer graphene sheets they achieve. Sometimes it is called as graphene oxide because on the surface of this graphene, there are different functional groups like COS group or OS groups. So due to that reason, oxygen groups are present. So they are called as graphene oxide, or if it is a bulk quantity, it's called as graphite oxide. Okay, so this is another approach by which we can unzip different nanotubes. Suppose we have a carbon nanotube, so we can unzip it because we have mentioned that this is a rolling of, if you're rolling this graphene sheets, you can achieve carbon nanotube. Similar way, if you have carbon nanotube, if you cut it or if you unzip it, you can also produce graphene sheets. If it is a multi-layer graphene, multi-layer carbon nanotube, you can unzip it to achieve multi-layer graphene sheets. If it is a single wall carbon nanotube, you can also achieve graphene, single-layer graphene sheets. There are different approaches for this type of method, like chemical approach. Another is the laser unzipping approach. So in the laser unzipping approach, we have to use laser beam to cut this carbon nanotube or unzip it. If you can unzip this carbon nanotube by laser also, we can achieve carbon nanotube or graphene sheets. So this is just a brief overview of different approach people use for this preparation of this graphene. I gave some examples. Similarly, other 2D materials already I mentioned. Other 2D materials also we can prepare by similar approach, like both top-down approach and bottom-up approach. Like same unzipping methods, CVD method like chemical vapor deposition method, electro deposition, solution-based method, micromechanical exfoliation, pulse laser deposition. All these are the widely used techniques or different physical and chemical methods to prepare these 2D materials for our respective applications. We are also doing some of these applications in our group to prepare different types of 2D materials. So this is about how to prepare this material by different approach. But once you prepare these materials, how to confirm whether this material is formed or you achieve some different material or it is a not pure material, or how thick, or whether it is a nanomaterials or not, whether it's a bulk. So there are different techniques to characterize this material. So first technique is XRD, X-ray diffraction method. XRD is not only used for characterizing 2D materials, but any nanomaterials or any material we can characterize by XRD or X-ray diffraction method. I think most of these students in BSc level might have studied what is XRD. So here, this is the machine, XRD machine. This figure shows the XRD machine. I think working principle of the XRD, all the students know about it. So XRD works on the Bragg's law, 2D sin theta equal to n lambda. So here basically we have a X-ray source, we have sample and then detector. I think some student is doing this line. This line I'm not doing, some student. Okay. So in this XRD approach, so we have X-ray source. So different types of X-ray source is there. So this X-ray falls on this sample, and they get scattered. Okay, so depending on this interference pattern, like if it is a like constructive interference, we can detect this light source after the scattering, and depending on this intensity change and depending on this atomic planes, we can achieve different X-ray patterns. So we have some standardized X-ray pattern which is already reported in literature. So we have to compare the standardized data with your data. So if it is suppose a graphene or carbon material, so carbon material will have a particular like XRD pattern. So if you can compare with your carbon material like JCBDS they are called, so you have to compare it. So if it is compared with your standard value, then you can confirm whether it is a pure material form or it's not. And sometimes if it is a very nano level thick, your XRD pattern, width of your XRD pattern will change and their intensity also will change. So from that we can confirm whether it is a nanomaterial or some other kind of material. So this is the Bragg's law, which all students might have studied. This is 2D sin theta equal to n lambda. So this Bragg's law is used to to do the X-ray analysis or XRD pattern analysis of this material. This is the Raman spectroscopy. Raman spectroscopy is the widely used technique for these nanomaterials and 2D materials. For graphene, this is the Raman spectra of a graphene. So they are like D band and G bands is widely present in the graphene sheets. So depending on this single layer or bilayer or multi-layer graphene, your intensity of this D band and G band will change. So by seeing this relative intensity like ID by IG, so from that you can tell whether it's a single layer graphene sheet or bilayer or multi-layer. So this black curve of this Raman spectra is shown. It is a bulk Raman spectra of a bulk graphite, and this some graphene oxide and reduced graphene oxide. And usually this D band, if it is very low, it is good because D band represents a defect related Raman spectra. So D band is less means your defect in graphene sheets is less. So that is the technique used to characterize this graphene and other 2D materials. This just I'm giving some brief about the different techniques, how to characterize. So this is the optical microscopy, another technique to characterize 2D materials. So you have to see the color contrast once you transfer this material to some substrate. People usually use silicon dioxide, silicon substrate to transfer this material. So once we have this material on this silicon dioxide, silicon substrate, so you have to see, you have to use a optical microscope, see the color contrast, how this color contrast is changing. So if it is single layer, the color contrast will be different than this multi-layer structures or multi-layer graphene sheet. So from that you can also approximately know, or you can tell that it is a nearly single layer or bi-layer. So then you go for further characterization like Raman or microscopy, electron microscopy, then XRD, all this AFM, atomic force microscopy. So all there are different types of techniques to further confirm whether it is single layer or bi-layer graphene. So this is the schematic of the atomic force microscopy. I think if some students are interested, they can go very deep to know about these techniques. These are like widely used techniques, and from internet one can get all these details. If you want to study more, you can search for it. So these are the techniques used for this characterization of this materials. So it is here. It is why it is called atomic force microscopy. So here, the force difference. What is happening here? We have a cantilever which is moving on the surface of your sample, and this is the arrangement, and one laser light will be falling on your cantilever, and deflection from this laser light depending on your roughness of the surface will be different. So when it is falling this laser light, so you have to see the resultant or reflected laser light, and you have to map it. So if you map the surface, you will get some kind of morphology or some kind of structure. So that you have to confirm whether it is a single layer or bi-layer. So if you are considering a single layer graphene sheet, it will be around 0.3 nanometer thick. So from this atomic force microscopy, you can also confirm how thick is your material. So from that, you can confirm whether it is a single layer graphene sheet or multi-layer or bi-layer. So accordingly, your thickness will change. So this is the atomic force microscopy of some of this material which was collected by atomic force microscopy. The image looks like this. So this is one graphene. Suppose you are telling single layer graphene. So if you make the height profile analysis, from this height profile analysis, the thickness will be around 0.34 nanometer. So accordingly, if it is 4 layers, it is multiplied by 4, like 0.3 into 4. So that much range, if you are getting the thickness, you can tell it is a 4 layer. Similarly, if you are getting bi-layer or tri-layer, you can calculate how many layers are present in your sample. So this is the very good technique to confirm how thick is your material or whether it is a different layers of material. So this is scanning tunneling microscopy. It works on the principle of quantum mechanics, quantum mechanical tunneling. So this is very I'm showing the technique briefly. If some students are interested or somebody is interested, they should go through more detail in literature. It is easily available everywhere. So scanning tunneling microscopy. So when this your tip is moving on some substrate or some sample. So depending on the distance between them, tunneling of electrons may happen, like tunneling from either from this tip to sample or sample to tip. Tunneling of electron may happen due to this quantum mechanical phenomena, and this we are measuring the tunneling current from this movement of your tip on your substrate. So that you have to quantify by different electronic arrangements and amplifiers and other electronic circuits to see the morphological view of this material. So it can give atomic level resolution of your material because these electrons are involved here, and they can provide information up to atomic level of your atom, how atoms are arranged in this material. So that kind of behavior you can get. So this is just showing some of this example or how this scanning tunneling microscopy image looks like. So this A is showing some of these seeds, nano seeds. So here, this if you are taking low resolution or low magnification of this image, it will look like this. But if you go on further magnifying this seeds, you can see all these dots are representing all these atomic or atoms of some material. If you are taking graphene, you can see atoms of carbon like this. So atoms are arranged in hexagonal lattice manner because this graphite graphene is hexagonal structure. So you can see this all these carbon atoms are arranged in hexagonal like positions. You can see. So from this you can see atomic level how these atoms look like this. So this is the one technique. Similarly, by transmission electron microscopy. So it is also another powerful technique by which also you can see atomic level resolution. It is called high resolution transmission electron microscopy. So similar to B shown here, you can also in HRTM analysis, you can also see this atomic level arrangements of atoms by doing this HRTM. This electron microscopy basically widely used. There are two types of electron microscope here, like scanning electron microscope. Another is transmission electron microscope. Scanning electron microscope principle is different than the transmission electron microscope. I will not go in detail because it is not possible to go in detail. So I'm just showing how this imaging of these nanomaterials looks in scanning electron microscope and transmission electron microscope. So first two upper images are showing this electron microscope or SEM, scanning electron microscope image of some of these nanomaterials, and this bottom ones are transmission electron microscopes, and you can see all these atomic level arrangements or atomic level images you can see by transmission electron microscope, and also it is known as high resolution transmission electron microscope. Okay, so this just briefly I gave some examples of how to characterize this material by different advanced techniques. Once you prepare some nanomaterials, how to characterize them or how to confirm whether it is a nanomaterials or what kind of material it is. There are different other techniques also. I'm not showing all techniques here. They're like, suppose what are the elements present in some material, how to characterize them. There are different techniques like electron diffraction, EDAX technique, electron diffraction, X-ray analysis technique, or you can tell mapping, you can do elemental mapping, you can do. Then XPS, another technique, technique is X-ray photoelectron spectroscopy. So by using this technique, you can also characterize your material. So once you prepare a material and you confirm that these materials are pure form, or what kind of material it is, whether it is a more defective or less defective, or if the impurities are present or not, then we go for different device applications. Because if the material is not good, your device performance or applications will not be that good. That properties also will be different. So there are wide range of applications people are doing. So here it is shown for different 2D transition metal dichalcogenides. And similarly, graphene already I mentioned there are a large number of applications people are doing because their properties are different. And here transition metal dichalcogenides like suppose MOS2, WS2 or tungsten diselenides, tellurides, different types of materials are there. So depending on their material properties, people are applying for energy storage, different sensors, electronic devices, photonic devices, optoelectronic devices, transistors. So all these devices are possible. So they use different fabrication techniques also to fabricate these devices. So this is about energy related applications of 2D materials, 2D metal dichalcogenides, graphene. So I'm just giving example. So there are large number of 2D material. People are exploring different energy related applications due to the energy crisis, alternate energy sources, renewable energy sources. People are working on this. So some of these energy applications, like if you are doing energy storage devices are basically supercapacitors, lithium-ion batteries, and sodium-ion batteries, aluminum batteries. So different batteries are there. And then energy conversion devices like solar cells, photovoltaics, then different catalysis related fuel cells, hydrogen evolution reactions people are working on. So different types of energy conversion devices are recently being explored to achieve alternate energy sources. So supercapacitor is it is coming from this term capacitor. Basically, all of you know maybe knowing about what is capacitor. So if you take a parallel plate capacitor, we have two electrodes. One is positive electrode and a negative electrode. So in between we have a dielectric. Okay, so dielectric is very important to store this energy at the interface because the charge get accumulated and they form dipole at this interface and charge is stored. Similar to this supercapacitor also involves similar type of phenomena, but it is basically electrochemical. It is called as electrochemical supercapacitor. We have here two electrodes. They are separated by a separator or the separator which is soaked with some electrolyte. So electrolyte is involved here. So this electrolyte can be either acidic or basic or different ionic liquid based electrolyte. So when you pass some voltage, so this electrolyte break and they accumulate on this electrode materials. And similar to capacitor, they can store huge amount of energy. So here we are using nanomaterials as these electrodes of this supercapacitor. So all these nanomaterials, suppose example we are taking graphene, they are having large surface area. So if you are taking large surface area, this capacitance is directly proportional to this surface area. So if you are taking a parallel plate capacitor, so capacitance is equal to epsilon 0 A by D. So D is the distance between the electrodes and A is the area. So since this area is very huge, so you can expect very high capacitance or high energy values for the supercapacitor, because in supercapacitor we are using nanomaterials as these electrodes. Okay, so this is just like current status of different types of energy related application. You can see the supercapacitor is now in the development demonstration in that region only. So it's not really applied commercially. Some places people are trying to apply for this different vehicles, cars, then buses. It is trying. Some countries people are trying, but it's in demonstration stage now. Supercapacitor. Some are available in market also. You can see if you search in Amazon, Flipkart, some supercapacitor also you can see. So they are not very huge as compared to the batteries. So this is now research is going on. It's a very new topic and people are exploring so different high performance of the supercapacitor compared to the battery. So how these supercapacitors are different compared to the battery and electrostatic capacitor? Whatever we have studied in BSc levels, you might have studied that is like electrostatic capacitors. So how, if you compare this performance of this electrostatic capacitor with supercapacitor, you can see this from this table, this performance. There are like different parameters: discharge time, charge time, energy density, specific power, then capacitance, and then number of cycles. So you see there in supercapacitors, this power density is very high compared to the battery and other energy storage devices. So they're like very high means it can have very fast charging and discharging. So if it is very fast to charge, so if you're using in your mobiles or any electronic devices, so it can fast very quickly compared to the battery. The battery takes a lot of time to charge it. So supercapacitor, if you can use, or people are trying to use, so it can charge very fast or very quickly. And also its energy density also people are trying to improve further. And so that it can be applied for your real electronic or personal computers, other electronic devices people are trying to explore. Also, their stability performance is very high compared to batteries. So that also we are trying to improve. So this the third graph below. You can see this is called a Ragon plot. So here it is power density versus energy density graph. So it is compared with the different energy storage devices like capacitor, symmetric capacitor, supercapacitor, asymmetric, hybrid supercapacitor, batteries, fuel cells. So you can see hybrid supercapacitor, people are trying to achieve very high power density compared to others. So this is very recent topic people are working on to improve this performance. We also work on some kind of the supercapacitor devices. So here is how to, I already mentioned how the supercapacitor works. There are different types of working principle. It's electric double layer capacitor, pseudo capacitor, or hybrid capacitor. So in electric double layer capacitor, what is happening? This charges from these ions, like charges from this electrolyte. Suppose you are using H2SO4 as the electrolyte. So when you apply voltage, the H2SO4 will break, and this hydrogen ion and sulfate ion, they can accumulate on this surface, like on this cathode or anode substrate. And this, depending on this accumulation, they create some electric double layer capacitor there. Capacitor, like one positive charge, one negative charge is there. So that helps to store the charge at the interface. So this is the working principle of electric double layer capacitors. In pseudo capacitor, the principle is different. Like the materials react, like electrocatalytic, electrochemical reaction happens at this interface, and this is due to this charge transfer process, they store energy. So basically, carbon-based materials are used for EDLC type of supercapacitor, whereas oxides, sulfides, selenides, they are pseudocapacitor. So the drawbacks of EDLC is they cannot achieve very high energy density because they are not, they have some limit. But carbon, due to this carbon-based material, they are highly stable. So they can be very stable for more than 1,000, 2,000, or 5,000 cycles. And there will be very little bit change if you use for very long cycles. But energy density is low in EDLC type of supercapacitor. But in pseudocapacitor, they are not highly stable, but their energy density will be very high. So what people are doing, they are combining both the properties, EDLC and pseudocapacitor properties, to make hybrid structures. And there are different types of supercapacitor devices, depending on their configuration or materials used to achieve high performance. So it can be like symmetric capacitor. If it is a symmetric capacitor, both your anode and cathode will be same, and we are using one electrolyte. But if it is asymmetric, in asymmetric type, you can use different materials. One, suppose anode is carbon-based material, so cathode we can use some pseudocapacitor material. Pseudocapacitor materials like suppose metal oxides, metal carbides, or metal nitride, sulfides. So all these are different polymers, conducting polymers. So you can use it. So once you are making this hybrids of this material, so it can give better performance in terms of energy density, power density, capacitance, cycling stability. All these are tunable by tuning the different material properties. Okay, so if somebody is interested, they can read a little more to understand all this. So already I mentioned, so there are different types of electrode materials for the supercapacitor application. So different nanomaterials people are trying to use, because nanomaterials having a lot of advantages compared to the bulk materials. So it can have, suppose you can take 0D nanomaterials, 1D nanomaterials, 2D nanomaterials, 3D materials, like that. So a lot of wide varieties of materials are present, and we have also done some of this work on different materials. So here is another type of supercapacitor that called micro supercapacitor. So this is very emerging topic in recent times. So this micro supercapacitor is, you have to make some micro patterns, and this can be used in micro devices like all electronic circuits. You can use this supercapacitor. So it can be by using this, you can make device very compact and very small. Okay. So this is a very recent topic people are working on to fabricate micro supercapacitor devices. There are different approaches to keep more details. So already mentioned, supercapacitor based on this hybrid or composite materials. How much time I can take? I will try to complete as soon as possible. So here what is happening? So all of you know about the story tortoise and rabbit story. So tortoise, if possible, tortoise can also win sometime. Rabbit can also win. If rabbit, if he won't sleep, then he can also win. Similarly, if you see supercapacitors, so already I mentioned there are different types of supercapacitor like EDLC type and pseudocapacitor type. They have different advantages. One is having long cycling stability, another is having high energy density. But if you combine them, like similar to your tortoise rabbit, if you combine them, so they can have high performance in any condition. Like here, if you combine this tortoise rabbit, so they can win all the time. So similarly, people are trying to combine different materials to make hybrid materials. Suppose you have a graphene, which is a very highly stable material, so we can combine it with some high energy density supercapacitor material and make heterostructures or composites. So that then you can achieve very high performance of this supercapacitor devices based on them. So there are a lot of advantages of these 2D materials. I will not go in detail. So we are, I think, running out of time. So already I mentioned. So here some of these device structures, how to fabricate in laboratory scale, we are doing in our lab. So we make 2 electrodes of these materials, then make compact and use some electrolyte and 3 electrode and 2 electrode configuration, then fabricate these devices. So these are the characteristics and data of the supercapacitor performance. We use cyclic voltammetry, charge discharge curve, and then calculate this how much energy is stored in these devices, and then see whether this material is good for energy application or not. So this is one example, tungsten disulfide, which is a layered materials. Tungsten disulfide with graphene based material we have tried. We have published long back ago in 2013, which is one of the first report we have reported in literature. After that, lot of work is already other people are also working on this kind of materials or other materials. So this is another example we have done, vanadium diselenide, which is another interesting material, which is metallic in nature. This is a layered 2D material. So we prepare this material by this hydrothermal or simple servothermal method and prepare these heterostructures or composites of this material. This we did some supercapacitor, coin cell type of supercapacitors, and these are some of those characterization or supercapacitor performance of these devices based on this material. So this is a comparison. When you do supercapacitor analysis, we try to first see how much energy or how much energy density, power density, specific capacitance, stability, all these parameters we test. Then we compare with the literature, like what is the range, how good is our data. So then we try to publish somewhere. If it is a good data, then we can publish in very good journals. And if it is a fast report, then you can publish in also high impact journals like you can see Nature, Science, Nature Materials.
Sir, sorry to disturb you. So actually आपन भॉइस टिके ऑडिबल होनी आपन टिके से टिके दी लाउडली टे कहबे और हम समझ सुई परिबा कहीं सम चैट बॉक्स से मैसेज आउछ जे ऑडिबल होनी सेतले आपन टिके सम डिस्टर्ब करले
हां सॉरी ओके सॉरी यो लाइन तो मोर आउ अल्प स्लाइड
ओके सर थैंक यू सर
So these are the some of this data which we have done. This is vanadium selenide multi-wall carbon nanotube composites, which we have also done. This is similar hydrothermal servothermal method. So this is the material how it looks like. So you see this is vanadium diselenide with carbon nanotube embedded. We do characterization of using scanning electron microscope, transmission electron microscope, then elemental mapping. So all this is the XRD pattern, X-ray diffraction pattern to characterize these materials. Then we do the supercapacitor performance. So from this we come to know whether it's a good or not. So then we do some theoretical analysis of our data also to support the experimental finding. We do some theoretical calculation to understand what is the mechanism, how it is storing the energy, and how further it can be improved. So all these aspects we analyze. What is the physics or what is the materials mechanism is involved, in this kind of energy storage performance, that we try to understand, and then this data is published. So similarly, another report we have recently published. This is ternary composites, vanadium diselenide with carbon nanotube and graphene. So all these three materials are combined to make supercapacitor electrodes based on these materials. So similarly, we did, and this work also published recently. Well, anyway, I will stop here. So this is just a conclusion. So there are wide range of 2D materials people are exploring for energy storage, supercapacitor applications, battery applications. Some of this material we have also tried to do. So this is some of the materials we have done is like vanadium selenides, sulfides, tungsten disulfides, vanadium sulfides, nickel sulfides, cobalt sulfides, and then other ternary sulfides, oxides we have done for different supercapacitor applications, and did theoretical analysis, experimental characterize and properties, and energy storage performance we do, and then understand what is the physics behind it or chemistry behind it. Then so this is like our students which they contributed for this work which we are doing, and some of my collaborators in different parts of world and in India also. And funding agencies, we get funding from DST, Department of Science and Technology in India, then UGC, CSIR, MHRD, BRS, which is also got some funding from our university. Also, we had some funding. So due to that only, we could do some research in this lab. So this is our research group, recent research group, which some of the students they contributed for this research. Okay, thank you for your attention. So if you have any questions, then I can answer some of you. Talk is over. So any questions?
Hi.
Okay.
I'm audible, no?
Yeah, you're audible. Okay, tell me.
Yeah, it's like not question. I'm just concluding the basic what you mentioned here for the students, like the two-dimensional material what we are discussing here. So as Dr. Raj showed the first slide where like the if you can cut, if you take a bulk material, if you cut it one-sided and you reduce from one side, then you can get a two-dimensional material. Like, and then if you reduce further, like you reducing from one side, then you have a two-dimensional material, like filling. And if you reduce from the both the sides, then you have a rod, carbon nanotube, and so that is like one-dimensional. And if you reduce all the three-dimensional, so like
it is
X,
like
Y, and Z.
Yeah. We are confining on different direction.
Yes.
If you're confining in one plane, it can have 2D structure. If it is confined in all three dimensions, so we are squeezing, so it can give 0 dimension, like quantum dots, particles, nanoparticles. So that can give different type of structure. So here in 2D structures, we are confining all these atoms to move in a particular plane. We are not allowing the atoms to move in any other direction. So if you are doing that, you can achieve this 2D structure. Nanoseeds, graphene. So these are the examples. Okay. Any doubts from students? Basics or something?
Yeah, because the people have to understand like what is the nanometer size.
Yeah. Nanometer is 10 to minus 9. So if I gave some brief because it is not easy to give so much. Anyway, that's why I covered what is material, what is nanomaterials, how to characterize them, what are the properties, and some examples I gave. So maybe I think something they might have followed.
Yes. Yeah, the basic understanding like students should have like, if you if you go to the lower dimensional metal, then you have more application point of view, because they can understand one simple thing what you mentioned about the surface to volume ratio. Means you have more surface now. If you cut it, if you have bulk metal, the surface what you are getting, and now when you have a 2D material or 1D material, you have more surface area compared to the bulk material. So you are allowing more surface area to interact you whenever you're doing some application like supercapacitor or solar cell. The same thing. So you have more surface area which you have allowing like more type of interaction with the system. So
Yeah. So
not only that, there is so many, yes.
So many other properties also will change. One example is the surface area. Similarly, their optical properties will change, their absorption, transmittance, all this will change. Electrical properties, semiconducting, metallic, so superconducting, all these properties can be changed. So depending on your nanomaterial structures, so it can be tuned. Okay.
So I am going to, I think, just add not only the nanomaterial range material, also in the time scale, where again I have to go to the nanosecond or picosecond or in femtosecond time scale. So it will be like both way you have to go to the reduced dimensional in time zone and in material zone. So same thing what you have mentioned here, going to the taking low dimensional material and then going to the lower, very lower dimension time scale to understand the property, particular the optical properties of the material.
Okay. Yeah. Anything? Yeah. You can contact me if any students want to know something. You can write to me also. My email and all. You can. I think
there is one question. What temperature does graphene oxide start to reduce?
Graphene oxide start to reduce.
Yeah. Yes.
Graphene oxide, yeah. So graphene oxide is basically their graphene sheets. There is some functional groups on the surface, like different functional groups, OS group or COO group. So these functional groups are there. So depending, you have to see at what temperature these functional groups can go away from this graphene oxide. So depending on that, your temperature also is required accordingly. So usually if above 200 to 300 degrees sufficient to remove them. So if you directly heat them in air, so they may burn carbon atom also. So to avoid this, people use vacuum or different inorganic gas, like inert gas like argon, nitrogen. So if you heat around 300 degrees, so they can be removed, all these functional groups, and you can achieve reduced graphene oxide by that. Yeah, somebody I think was doing some pen marking and showing in slides. So please try to avoid this. I think
yeah, I think
I don't know whether purposefully or by mistake. So please avoid. Okay. Okay. Anything else?
Okay. I think there is no more questions.
Okay, so maybe you have to start also.
Oh, I think you have to unmute your writing. Yes, unmute your.
Remove, no? Is it showing?
You are done. I think, yeah, this college they are talking.
Yeah, is it removed? My slides, I think it's removed, no?
Yeah.
Yes, sir. I think there is no other questions, so we can go for next session. So I invite Deepika, a student of our college, to coordinate the program.
Thank you, sir, for such a educational and special thoughts. Now, I would like to invite Dr. Manas Parida, sir, to deliver his thoughts towards the students. Please, sir.
Thank you. Thank you. I think I am very much thankful to Dr. Ramesh sir for inviting me not only inviting, at least searching, finding, reach out to us to arrange this type of webinar. And grateful to principal of the college, the Professor Das, for inviting. Yes, I can audible, no?
सर टिके साउंड आपण टे वॉइस टे भन टिके से बड गन टिस
Okay.
अधिक करे टिके सुबियो समथिंग सर
Okay. Okay. So maybe I can complete last. Okay. So yes, I'm going to share the screen. Now I am audible nicely. Okay. Okay. So I'm sharing my screen here. Let's see the presentation. Okay. Let's see if I do the means you can see everything there. My presentation is visible to everybody. Correct?
Yes, sir. Yes, sir.
Okay. Okay, so the I'm continuing with same type of material, but this is little different application. So here it is like perovskite, which is a solar cell based material. And if you see this image, I think everybody knows about the silicon solar cell. What about the, yes, because this is now mostly available in the market, commercially it is available. So let me start how, okay, this is my outline of the presentation. I will give basically the introduction to ultra-fast processes. As I mentioned, not only we are going to work in reduced dimensional material, but also in the reduced or I can tell ultra fast time scale, means it is in picosecond, femtosecond or nanosecond time scale. So it is two type of new new system, I can say, for students. So I will give some few research outputs of my previous works, and so coming to the solar cell, I think everybody knows about the silicon solar cell. So how the silicon solar cell works? So if you know this is a so I can this is a solar cell. You know the silicon what you can see on the road using for getting street light, and so here what you do when you put the sunlight. So you know there is two type of silicon, like P-type silicon and N-type silicon. So one is electron carrier, another is the hole carrier. So what you have to do when you are putting the sunlight, so there is possibility of electron movement, I can tell electron transfer. So one way it will be like if you see the left one, so top part will be electron flow and the below part will be hole flow. So when you separate, like you separate the charge, so and then at the end you collect in a circuit and you collect the charge. So then you can see you got the light. So in this way, solar cell works. This is, so here, what our research interested here, because silicon is very costly and also the efficiency wise worldwide it is not that much helpful, although till silicon is the all over the world till now, other things have just coming out. So in the I'll discuss more this particular material, which is perovskite, which is more advanced in a in material community, which is used for solar cell application. So the understanding more detail about the solar cell, if you see there is a cell, which designed by us. You know the inside structure where I am showing the electron and hole, where the materials are there, means whatever material you are selecting, whether it is a nanomaterial, mostly you are taking the 2D dipole material. So and then you have some electron transport layer, hole transport layer, and then on top of that you have to put some metal which should be transparent for collecting the light. It is basically this system. If you see, is my mouse also, you can see my mouse, like I can pointing my mouse, and is it visible in my mouse?
Yes, yes, it is visible.
Perfect. Okay, so I can point nicely. So the center part, if you see, this is the, I think mostly I am going to discuss only this part where we have selectively choose particular type of material from where you can, this is known as active material, from where you can generate electron and hole. So I think this structure, I think no need to more confused about this, how this cell looks like. If you compare, I just for for comparison, I just took a cake. We have so many different colors. Whether it is a chocolate cake, whether it is some other color, but there is, and of course the thickness of the layer here is almost looking like same, but here it's not that way. It's depend upon which layer should be thin, which layer should be thick. So it's depend upon how you are synthesizing or how you are fabricating the device. So, this is the one means how the solar cell looks when you made in lab. Of course, the dimension here in cake, okay, you have in millimeter, right, or of course in centimeter, but here, of course, we are dealing with nanometer. So basically, what do you understand till now here? Like you have to insert light on sunlight, you are putting on the solar cell material, then you have to electron flow. So you have transport electron, and of course, same way you have to transport the hole. And so what is the electron transfer? So selectively, that means the material who will give electron, that we can tell this is a donor material because it is giving donor electron, and the material who will collect the electron, that will be like acceptor. So we have to selectively choose these two materials, which material has to give the electron and which material has to accept the electron. So this will become the electron transfer process. So once you have electron transfer, so that it means the main mechanism is you should have a very efficient electron transfer when you are thinking about making a solar cell device. So I think this picture can give a little more idea. So when you excite, you see you have seen this figure, like when you excite, so electron moves. So it's moved from donor to acceptor. And then second, once electron has moved, then you have like charge transfer. So you have electron comes from donor and moves to the acceptor. And after movement of electron, means after charge transfer, then you need to clearly separate them, and you have to keep them in longer time. Then only you can connect with the circuit and get the current. So that's why you have to separate. You have to separate the electron and hole. Like once you separate, and then you can put a external circuit where you can collect the charge. Yes, it will go to the circuit, and then you can collect the charge. So this will be like charge separation. So basically, what you need fast electron injection. Not only the fast, you need efficient electron injection, which is like after that you need efficient charge separation, and then at the end you need efficient charge collection. Then only you can get the electricity or energy from the. So all these process, electron transfer or electron charge separation or charge collection, if I think it's very simple to understand, this is happening in very ultra fast scale, means it is happening within some nanosecond or picosecond or femtosecond time scale. So how to measure that? How to measure that? So I think this type of work started when Professor Jewell, I think he got the Nobel Prize. Maybe I can minimize this. Yes, he got the Nobel Prize on 1999 for the measuring the how the atoms molecules moves in a chemical reaction, because when you have a chemical reaction, whether it is a endothermic or something like that, there is a electron transfer, and so how the electron moves means how the atom moves. So I think he has done with laser, of course the ultra fast laser, and he got the Nobel Prize for that. So how to understand what type of process happening in the this particular time scale. If you know in the left side here, the particle physics, which is we have dealing with like 100 giga electron volt energy, and nuclear physics of course in range of mega electron volt energy. But in atomic science, like in material science, what you are dealing, we are dealing with some electron volt energy, and the time the nuclear reaction and this thing, even if it is going super fast, like 10 to the minus 22 second. But still, this type of process, like electron transfer, energy transfer, I will discuss more about this, which is happening in the range of picosecond to femtosecond, or maximum going to the attosecond, like 10 to the minus 18 second. So these are the processes which happens in very ultra fast time scale. So that's why we discuss about these are the ultra fast processes. Yes. So once we excite molecule or excite any material, excite means when you put some light, like this one. When you put some light, we know once you put some light, then it will excite. Excite means it will absorb some light. So that is known as absorbance. I think this is very simple things to understand. So once it will absorb some light, then that particular system, that particular material will like transfer the electrons or ions to the excited states. Excited state, if you see the figure, so this is my ground state. All the material wants to stay in the ground state. So once you excite it, means you put in some light, so it will go to the excited state. Excited states means it will be not stable state. So definitely it in high. So this S1 is first excited state, S2 is second excited state, because if further you excite something here, so then the atoms will again further go to the higher excited state. So, but later on, we know that atoms or molecules or electrons, it cannot be stay in excited state. It has to come back. Okay. So the comeback processes, there is so many processes happens here. One is internal conversion. Internal conversion, I think this color you can see, yellow is yellow. So if the electrons will transport to the higher excited state to lower excited state. So this process is known as internal conversion, because inside the system, inside the excited state, it is coming back. And then the most important one, I think we know that fluorescence or phosphorescence, like that. When the excited electrons will come back to the ground state, so it will give light, which is emission, which is I can tell fluorescence, or if it is delayed fluorescence, means it has to go to the singlet state to triplet state. I think singlet, triplet, I think maybe quantum mechanically we can understand. When we have seen, we can add, and if like half, then we can add, and it will become like 1 and 0. So on that becomes, so the total quantum number can give you like 3 or 1. So on that way, whether the particular system can stay in singlet or particular state can go to the triplet. So triplet physically, if you understand, so the emission, it will be not directly come from the excited state to ground state. It will go through the another state, which is like triplet state, and coming back to the ground state. I think this is similarly when we deal with understand about the laser also. We have like metastate, and if you come into the metastate, and it will come to the similarly. So so not only that, this will, I think that process is known as intersystem crossing from singlet to triplet. So there is so many other processes also, like what we discussed till now: electron transfer, proton transfer, energy transfer, or delayed fluorescence. So these are this type of technique or processes. How you can measure it means how you can do. As you know, these are ultra fast scale. So that's why we have to set one setup, which is known as pump probe technique, or it is known as transient absorption technique, where see, so you have a material like sample A. So what I did, I just excite with one laser pulse. Of course, this is in femtosecond laser pulse. Why I am using femtosecond? Because the process you are going to catch, process you are going to photograph, that will be happening in femtosecond time scale or in picosecond time scale. Just like this process in the left side, you see, the solar uh, glasses, sun gases. When you go out and if you have the sun, then your color is changing automatically. And then once you come back, again it will be come back to the normal color. So this type of process, because this also happens in seconds. Okay, so but what is happening here, as I mentioned about the electron transfer, like hole transfer or charge transfer, this is not in second, even if it is going to the nanosecond or in femto or picosecond. So that's why we need a femtosecond range pulse or laser, which can go and capture that process, not only like the spectral feature of the spectrum, also the time scale, means how much time required to coming back to the ground state. And how we do that? We send another light, with delayed time, time. So, and we just delayed the time little, and then we take the every time we delay little and we measure the spectral feature, and we see the time, means how much time it required to come into the excited state to ground state or whatever process is happening. So we have like time delayed, and we have which time delayed we measure the spectral feature, and the third thing we measure how much time required that process happen in that measurement. Okay, so basically this experiment results I am going to show just only this one. I will not expand more. So this is like technically how we connect it, but the understanding is simple. So we have a pump pulse, you excite the material, and so once you excite, the electrons will go to the higher excited state, and then you can measure. So because how you can measure? The simultaneously, which time interval you are passing another light, probe light. The probe light will act as a detector. So he will see how much electron has gone to the excited state. And then, and what will do, it will differentiate. It will subtract, the excited state absorption and the ground state absorption. So once you subtract, so, and then that result maybe we'll see. So once that will subtract, then we have a subtract absorption in y-axis, and then on x-axis we have spectral range, like the particular wavelength where we are measuring, or the time interval also. So these are the processes which happen in which time interval. On that basis, we have selectively choose which type of like laser you have to going to use, whether you are going to use a nanosecond laser, whether you are going to use a picosecond laser, or you are going to use a femtosecond laser. So on depend upon that particular experimental setup, you are going to measure this type of particular processes. Okay, so I will start from the one two-dimensional material, what graphene, like Dr. Rao told about so many, how to get, how to synthesize. Maybe the graphene, you can see clearly here, the figure A, where it will be very nicely carbon aligned graphene, the hexagonal structures, and then, and along with that, there is a functional group in the, on the surface of the graphene, which is carboxylic group. So this is a negative charge group. And then we have here one like molecule, which is known as porphyrin. If you see here, there is a cavity here, and there is a porphyrin rings, like parallel rings, which have nitrogen and positive charged rings are there. So what basically here we want to study, we want to see like how the graphene and that particular molecule they have interaction, and how the electron transfer happens. So what we do, this is happening in solution mode. So you somehow you bring porphyrin and graphene close to each other. So how they will interact? Because if you see the porphyrin has positive charge in their rings, and graphene has negative charge in the surface, which is the fibrously functional group. So when they come close to each other, so they have a electrostatic interaction between them. So that's why they come too close to each other. That means that's why they have a pi-pi interaction, which is like surface to surface interaction. You can see this picture, the figure A, where it is sitting on the top. Okay, like how, and then as and then once you excite, you put laser light, like, and then you can see the electron transfer happening. Okay, so how we will see that? If we have to see the I think this graph one. So the first graph is the absorption graph of the black color one, the absorption graph for this particular porphyrin molecule, and there is a Sweret band around 420, and there is some Q bands around 500 to 600, and then you add graphene inside that, and again you measure the absorption. This is very simple experiment. Means you have to just put sample and put the light, and you see how much light is absorbing. Of course, where the absorption is more, so that means at that point it will absorb the light more. So that is so that depend upon, if you take silicon has a band gap around 1.1 electron volt. So if you put light around 1.1 electron volt light, then it will absorb that. So you'll get like at 1.1 electron volt. If you convert 1.1 into wavelength, we have to divide, like, the E is equal to SC upon lambda, which is like 1240 electron volt upon lambda, which and then we can calculate where it will absorb. So on that basis, this particular experiment happens, like where it is observing. Okay, so once you added some graphene into the porphyrin, that means you are bringing close to each other. You can see the spectral change here. In the figure A, the black becomes red, and then blue, then orange, then it is, and you can see the change in the spectrum. It's slowly decreased and shifted, and then started slightly increase, and there is another peak happening. So this particular peak is now here by interacting with the graphene. So what is happening here? And if you see here also, there is 1, 2, 3, 4 peaks, and then now it has become 2 peaks, another 2 peaks and 1. So basically, the experimental results we analyze like this way. And this is the absorption graph, which is very simple to understand. And this is the emission graph. Emission, particular has where that particular molecule has emitting. So it is emitting around 650 or 670. And then once you add graphene, then it has going slowly quenching. This process is known as quenching. The same, this is not quenching. This is like reducing and shifting, but this is absorption process. The emission, when the emission peak will be systematically decreased, means, so if this process is known as the emission is quenched. That means in normally you can tell that emission has gone, like it is not that much emitted now. So that makes sense because and now it's not only porphyrin, because it's combination of porphyrin and graphene. And as we have some indication here, the shifting, so this known as they have a very good interaction. I can tell that the term they use, it is like complex forms between graphene and porphyrin. So they have a complex formation. So they have a due to electrostatic interaction, they have a very close to impact each other. So there is a pi-pi interaction, like the body stay with each other as you see in figure. Then there is whatever electron inside, the electron will be transferred to graphene. Okay, because why I'm doing this? Because we have to understand how efficiently we can move the electron, okay, and which is useful for our solar cell application. So understanding this one more detail, what we do next experiment, we just remove the positive charge here. Okay, if you see here, so there is no no positive charge in the perfect. Okay, there is no. If you see here, the nitrogen has positive charge here, and here the nitrogen has no charge. So this is neutral. So once it will be neutral, so we cannot see any change in the absorption or emission. That means, so the main idea here, the electrostatic force. So as they don't have now any electrostatic interaction, so so they don't have any interface between them. So there is no electron transfer happening here. So we make a cross here that there's no electron transfer. So this particular design is giving information how the to give a picture like how the electron transfer happens here and how it is not happening here. Okay. And the second thing is if you see the rings, the porphyrin rings, here it is flat and here it is like little bent. So it is because in solution they have interaction has like they have a movement. That movement gives also like they have a internal electron transfer between the cavity of this porphyrin to the rings, and that also disturb, or I can tell that also. So the understanding that we'll do another experiment. So okay, so this one if I'll compare with this, the second graph if you see here, this is the same graph in the porphyrin, but here it is not only the observance, we measure in change in observance. As I discussed earlier in that particular experiment, so you excite and then you send the electrons downstream to excited state, and you take the difference between excited absorption and the ground state absorption. So once you take difference, when you send electrons more from ground state to excited state, and at where that particular light is absorbing, at that particular where if you see here this particular point like 420 where the light is more absorbing, here it is not absorbing more. So the 420 light is absorbing more, that means the absorbance peak we got here. So similarly if you see the same absorbance deep we will get here, because once you are taking the change in absorbance, so where the absorption will be more. So once you subtract from higher state to lower state, so you will get a negative signal, because you are subtracting from higher number of electrons minus the lower number, opposite, lower number of electrons minus higher number of electrons, because at that particular point you have already sent the electrons from the excited state. So you have more electrons in the excited state. And similarly, this range where the absorption is less, you will get more or less excited state absorption, means more positive signal. Okay, so these two experiment I think I will discuss all my results. So this is simple normal absorption. You take a lamp and put the sample and you pass the sample, pass the light through the sample, and then you see where your light is absorbed. Very simple. And of course you put a detector and then you will see where, and then the same way, but here it is a little technical where you using two lights. That lights are not lamp lights. You are using like lasers, like picosecond and femtosecond laser. If you see here, these all the time delay I measured here in picoseconds. Okay, so so the same technique, the same type of measurement, but you have using two lights. One is probe light, another is pump light. And with pump light you are exciting, and with probe light you are taking the pictures, okay, of this picture. And as I mentioned, I am dealing the time like 20 picosecond, 40 picosecond, 60 picosecond. So with each picosecond time interval, I have taken the spectral picture, spectral information from the system. So what is the conclusion here? If you see here, so within 200 picosecond time delay, the spectral picture has not changed much. Okay, but when I add, this particular molecule, porphyrin with graphene, in there, you see the, the picture has completely changed between these two. You have, there is a very big excited state absorption here, which compromise come from here and comes from here. Okay, so initially, so this words comes from here, but now this words comes from here. Okay, because you added the porphyrin, graphene here, and not only that, you can see the change in the picture with time. So it is coming from the higher to now lower, and the same thing and the same thing. So this is we know as, the like how much time required to electron come back from again from the higher state to lower state, from the coming back to the ground state. So that time is important. That time we are going to measure. That's why we are using a ultra-fast laser here. So as we see here, in this particular measurement, we don't have any change with this particular 200 picosecond time delay. When we delayed the probe light 200 picosecond, we cannot see much change here. But when we delayed 200 picosecond here, we can see clearly change. That means here, when you have a graphene present in the system and you have electron transfer, and then you know how much time required you have to do coming back to the ground state, because you know that is never any state can never stay in excited state for long. It has to come back to the normal state, ground state. So that's we are measuring here. Okay, so I think this type of result I'll show maybe 2-3, and then we can finish. And okay, so what about here? If you see, the only difference between this and this, here we don't have this one. We don't have charged porphyrin, so we don't have any electron transfer. So that's why you cannot see any change in within this time interval. You cannot see any significant change as you see here. Okay, so you see within the 200 picosecond, the electron completely recombine, or I can tell it will completely come back to the ground state. But here it is still in this excited state. Means it will take longer time to come back. Okay, so means this. So the final conclusion is like that. So you bring porphyrin and graphene close to each other. They have an electrostatic interaction and they have a pi-pi interaction. And then from porphyrin cavity, there is electron transfer from porphyrin to graphene. And then you measure how much time required to electron come back to the ground state. Okay, so in this way. Okay, so what we did here, we if you see this particular picture, if you see this is the porphyrin, this is the graphene, this is the carboxyl groups. We are having the closing when they come to each other, they have the electron transfer. So what we do a little bit extra, the porphyrin ring, we know that they have positive charge. So what we did, we put some cyclodistin. It's also technically we just close the rings in another molecule, which is beta cyclodistin. This is this type of structure. So once we close, as I mentioned, the ring has property that it will in solution it will vibrate, of course, and then they have a intra-electron transfer. Means the electrons stay here will also go to the here. Okay, means to the ring. Okay, so and now we saw that electrons from here also we are able to move in the graph. Okay, so by closing this, means by closing or by encapsulating the rings in this beta cyclodistin, what we did, we make a disturbance between the electron transfer from the cavity to the rings. Okay, so what will happen once you make some disturbance, then that means all the electrons you staged here, means all the electrons have localized here. So you have now more electrons which will move to the graphene if you make again that interaction. So from experiment we have to do similarly experiment, and then we can start claim our result. So you see similarly absorption data what I present here. So porphyrin, then I added graphene, then you see there is a little bit change here in optical band, and but almost remains same. But here you see the emission, this is got enhanced. You see that when I add graphene, you see there is a quenching, but here it is enhanced. That makes sense because we know when adding cyclodextrin, because you are disturbing the structure. Okay, so by disturbing, there is this type of phenomena can happen. And then what we do, just comparison point, we just add a graphene in both the case. Means one we don't have the cyclodextrin, and one we have cyclodextrin, and then we add a graphene. So here what will happen? The similarly we can see. This is for porphyrin, the ground state bleach. What I am talking about this, and this is here because once you subtract. This is what you see. This is we have done in longer time scale, in nanosecond time scale. Okay, so once we compare in longer time scale, this is porphyrin, we know it will not recover very fast, it will take time. And similarly for porphyrin beta cyclodextrin also same thing. And if you compare these two, you see when there is porphyrin and graphene, and here porphyrin, cyclodextrin and graphene. This is like hybrid composite, and this is like only two, porphyrin and graphene. So if you see within 1 nanosecond, it has recovered only 20%. Okay, means the 20% electrons have come back to the ground state. But if you see in that particular time scale, in presence of beta cyclodextrin, it has completely recovered. Okay, like all the absorption, because this is just a absorption. What we are seeing here or here. Okay, because this band is around 450. You can see that is same thing here. Okay, so this band is here, okay, and this band is here, means this one, okay, and you can see the shift also from this to this, okay. So okay, these results will you no need to worry about more about how to get this. So the basic understanding what we got here. So the 20% recovery means the 20% charge recombined from ground state to ground state within this time interval. But here within that time interval, it is like completely recovered. Okay, so this absorption band, which is I told about like ground state absorption, which is recovered, like completely recovered. So that makes sense because we know that in presence of cyclodextrin, it has encapsulated the rings, and that's why you have more electron inside, and then it moves to the when you move the graphene, then you have more electron transfer here. Okay, so why we do that? If you see the clear picture here, so when you don't have beta cyclodextrin, you have electron transfer without that, but you have more like efficient. It is less efficient, this is more efficient. So these are the techniques, like how you can, because as I mentioned, if you need a better solar cell device, when you are doing it silicon, or then you are going to two-dimensional material or any low-dimensional materials, like, and then there is this, I'm going to start perovskite material. So all these things, what you have to know? You have to know, like, you should have a efficient electrotransfer. That is the first thing you have to do. And then later on, you should have efficient charge transfer and separation, and then you have to efficiently, you should collect. Okay, so that's why we have to clearly understand how one like this particular research, in there you have a idea like how you can tune the electrotransfer process. Okay, so in not only like you need more electrons for your solar cell application, you also know like efficiently it should transfer, and then you should have know that it should stay for longer time in which is known as diffusion length, like how far it can go. On that basis, everything, all this explanation will, or all this information will give you how you can get a better solar cell device, because that is your goal at the end. Okay, so perovskite, this is I think maybe little newer for students. Like perovskite is any crystal structure. I think solid state physics, you have little bit idea about the crystal structure. So you have cubic crystal structure or hexagonal crystal structure. So this is this is just a name, like this is like particularly perovskite crystal structure. So perovskite is not a single material. So any type of system of can give this type of structure. Okay, crystal structure. So what is A? A stands for cesium, or this is CH3NS3, which is an methyl ammonium, and X stands for iodine or bromine or chlorine. So that means you take anything, you take cesium here, you take lead here, and you take okay, you make a combine, you get a perovskite crystal. Okay, why we are doing that? Because it has a wide band gap. Because you play with the composition, then you have a very, because solar has a very broad band gap, so you need a that much tune band gap material. Okay, of course the production is highly simplified now, and high manufacturing yield, and of course you can make rectangular panels like what in silicon you have seen in the road also. So this although the solar cell, like not solar cell, like wind or coil or everything, they are providing electricity or energy. It has started 50 years back. So the solar cell system starts, I think, after 2000. Yes, slowly it's building off. I think now in 2030, I think there is this particular company, Oxford PV. It is just 2 kilometers away from here. So this particular company is now started producing, not yeah, producing. It's not commercially sale till now, but they have given the high efficiency solar cell material, or reported, I can tell. It's like around 28 now. So it has increased. Recently, there is a paper came on the solar cell based technique, which is, they used, I think America sent one yes, rocket to the space, and they have used this perovskite and organic solar cell in the rocket, where the in space it is extremely conditions is very extremely high because and you don't have direct sunlight also sometimes. So what they use reflected sunlight from the earth, and using that they able to get the electricity. Means the space also got light from this solar cell. Yes, they have used this. Okay. So what is perovskite? Simply what I measure, what I show the optical absorption graph. I will just show same thing. One optical absorption graph, like it is absorbing here. Similarly, if you know silicon also around if 1.1, so it will around 1000 in IR, it will absorb. And here it is also similarly, it is absorbing around 800. This is the absorption graph, and this is the emission peak for this particular methyl ammonium lead iodide. Okay, because as I mentioned, iodide can become chloride, methyl ammonium can change to cesium, you will get a particular crystal. Okay, so this is the film. As Dr. Raut already mentioned, you need a two-dimensional system, then you have to make a film. Okay, that means if you're taking three-dimensional material, you just cut it and you make a film. And as she mentioned, there are so many techniques. It is done in spin coating technique. Spin coating technique means is a solution-based technique. You just mix this, technique chemicals, and then you just spin coat. It's speedily it will be spin coat on the surface of the substrate. You take a glass substrate, and once you do the spin coat, and then you can see this type of film. And of course, there is so many other parameters like how much thickness needed, and how much depth, and how it will absorb. Okay, and particularly as I am more interested to see the optical properties, so that's why we are also we don't want to make very thick film. So, and we have to see, and of course we should have features. It should not be very thin also. Anyway, so you see this particular absorption band here, we can corresponding to the absorption deep, which is like I mentioned, like change in absorbance. And of course we monitor the recovery, how the excited electrons come back to the ground state. We can see that, and of course how much time it is taking. Okay, and that this similar graph can also represent here in this will be like the kinetics. I can tell that how the kinetics means this will give you how much time exactly required to the coming from the excited state to ground state or the ground state recovery. So, and here what we did is we play with little bit laser power. Okay, when we are using very low pump fluence, means we are giving very low pump energy. At that time you see all this means there is no change in the recovery, means it is almost same. The solid line here, it will be like theoretically we just feed it, means to see the how much time required, that parameter to finding out the timing constant like t1 or t2. It's depend upon how it is fitting, and the dot line is the experimental rate, what we got from the experiment, as I mentioned the pump probe technique there. So you are excited with the pump and then you take the picture photograph with probe. Okay, but once you have higher energy, like higher pulse energy, then you can see there is a faster recovery. Okay, means the it has, you can see there is a change, means it has increased rate of recombination. Okay, to understanding that also in source time scale also you can clearly see there is a increased rate of recombination. Recombination means we know that every when you are exciting electrons, you are going to excited state, and definitely it has to recombine. It has to come back to the ground state. So that's why I'm mentioning that process like when a recombination. Okay, so to understanding this, like how the laser fluence, like if you increase the laser fluence, it is affecting the feature, you know, it is affecting the recombination rate. So to understanding that, what we did the similar measurement, but not only the absorption spectrum we monitor, we also monitor like PL spectrum. We know the same absorption PL, and now this is like PL recovery rate. Like I can tell you in that way, like this is comes from like single photon counting technique, TCSPC, where we can measure how much time required to the compared to 1 PL like emission also. But here it will be very simple technique one we use, like just putting the laser light and we measure the emission. So you see, once we increase the influence power here, we can see there is a enhancement in the secondary peak. Okay, so this I think for students it will be really interesting to understand one simple thing. So you are increasing the pulse light here, laser light, and slowly you are increasing one particular band here. So if you understand laser, the laser also happens same thing. So you have to pump. So you pump something, then at some point you will get very intense light, because you know there is so many you know multi-photon absorption inside the cavity of the laser. That's why your input light is very less, but the output light is very high. Okay, so it's same thing. So this is like once you increase the pump intensity, so somehow you are getting very highly magnified amplitude-wise emission. So that means you have a emission, or you can tell a magnified emission, or I can simply tell this is a lasing process. So I think this is the one region why you have a faster recombination, or why you have this type of behavior here. So yes, so this is also, this is not like this one also we checked for a solar cell point of view, but here not only like solar cell, this is also giving you lasing point of view. Like this material can also use for your lasing application. Okay, coming back to the again your solar cell point of view, you need to see how the electron transfer happens. So again we play with the composition here. So here this is cesium layer bromide. Okay, as I mentioned earlier, like we have so many different composition perovskite. So here also you can see the nanostructure materials, as Dr. Raut also showed, like this is the transmission electron microscope images, from where this is very high resolution microscope, where you can see the images, what type of crystal structure you have. You can see clearly, you can see the crystal planes. I think this will be more interesting for students to see this type of like, you know, these are the like crystal planes. And even if you can measure what is the interplanar crystal planes distance, you know, like 0.58 nanometer, you can using this HRTM, you know, the 10 image. So using this, you know, you can measure what is the distance between two crystal planes. So here is the similarly, you can see the absorption and emission. Yes, this is the absorption. Okay, the black one, which is your undoped perovskite, like sodium bromide. And then there is one technique we doped with a little bit with bismuth. And you know, when your doping concentration is less, so there is a shift to the red shift. Okay, and once we doped little high, so there is a blue shift. What is the red shift, blue shift here? Because you know, the red shift, I mean, there is a change in band gap. Okay, why? That? Because you change in band gap happens because when you have size changed. Okay, when there is a, you know, you have bigger size to, you are going to the nano size, so the band gap slightly increases. Okay, the similarly type here, of course, here there is no crystal change, so the doping has not created any type of crystal change here. The optical behavior has changed here, you see. So initially it will be red shifted, and then after that it will be blue shifted, and the emission every time you dope something, it's quenched and after shifted. Okay, so why this is happened here, what we understand because of the formation of the trust. Okay, maybe next slide I'll give little bit more detail about that. But here again, the pump probe technique you can see here. In the undoped nanocrystal, again we measure the optical absorption, change in absorption using the pump probe technique, and we see how much time required it will be recovered, like 28 nanosecond. And similarly for doped one, it has become slower to coming back because it's 28, because here the complete recovery is taking like 97 minutes. Okay, so, and that also you can see here, this will be like how much time required to recombine, and you can see that it is slowly, the doped one is taking very less time, but sorry, undoped one, but the doped one, it has the recovery time constantly increase. Okay. Okay. Okay, so, and then if you go to the doped one, if you compare with undoped and doped one, in doped we already said like the doped recombination is taking higher time. But if you compare with the PL lifetime, this is the absorption lifetime measured here. It is like, as I mentioned, like the emission lifetime. So the emission lifetime is always gone to a faster recombination rate. Means it's decreased. So here it is increased, and here it is decreased. Okay. So because these are two different, because in absorption time constant means the transient absorption, but here it is PL like that. So how we explain that? So this is, if you see from this image, this is undoped one, you know, the band gap when you excite. So when you have a doped one, so there is possibility there is some trap states. Okay, means some impurity states is created here. Okay, in the excited state. Of course, these are not created inside the crystal. These are the you know, the in the excited states. Okay, once it is created here, so that means the electrons may be staged here in the structure. That's why your recombination time is increasing, but emission time, now emission time is, it is coming directly to here. So that's why the emission time is decreasing very fast. Okay, so this also, and then when you have high dope concentration, maybe the trap states are overlapping on the conduction band. That's why you have, you know, very longer time required to recover the electrons from the excited state to the state. So the impurity levels, or what I am telling to structure, it will be the below the first excited state, and in high doped it will be the higher the excited state. Okay, as I mentioned in below, we have a ground state and we have excited state, and now we are dealing with this excited state. So I am telling the trap states are maybe here, or in high doped maybe it is here. Okay, so on depend on presence of the trap states will modulate thing, or it will the tuning the time required for the electrons coming from the excited state to ground state. Okay, so for application point of view, we added the testosterone and ethylene, and we can see here. And then we can see when we checked with testosterone and ethylene, which is accepted here. Okay, so this graph, this is the undoped band gap, what I saw. This is the doped band gap, what I saw. So in undoped, when we put a acceptor, just like the first presentation where I showed porphyrin and graphene. So instead of porphyrin, we have peroxide now. Instead of graphene, we have a well-known acceptor, which is the testosterone. So this has band gap. It's not a molecule, that's why we can calculate the moments, the high the oxygen state and the low oxygen states. So here, so we can calculate this value, and then we can, there is known as another thing is known as free energy, like Gibbs free energy, which will give you the information how the electron transfer can happen. Okay, so that energy, if the difference between these two, like the conduction band energy and the LUMO energy, if they have a strong difference, then this will use as a driving force. The electrons move from the conduction band to the LUMO level of the testosterone. So that means due to the increase in the driving force, if you see the band, this one, because this is minus 3.1, this is minus 3.03. So definitely the because of the presence of trap states on the surface on the higher excited state, so you have a clear difference energy difference between the conduction band of here and the LUMO level, and that's why you have a more efficient electron transfer. Okay, so this way this is the how the carrier dynamics, or how the the electron transfer process happens for the, because you have to understand like how it will be used in device when you make the device. Okay, so that's why in presence of doped you have more efficient electron transfer due to the change in the driving force, which is Gibbs free energy, which is more here in compared to the on-doped one. Similarly, not only the doping, we play with a little bit with here with the size also. Okay, this is plate, which is two-dimensional material. So these are the plates, and these are the circles. This is more like spherical surface of this will also we change a little bit here the methyl ammonium lead bromide peroxide. Okay, so this with playing with three different shapes, like there is a plate structure, there is a spherical structure, and there is a cube structure. Okay, and here if you see the plate and then spherical, definitely we discuss about the of course the with the band gaps, like the change in the energy levels, and also we have the basic understanding, we have more surface area here in plate also, but in cubes maybe there is a little less surface area compared to sphere, because the particle size will be low here because band gap is less here, sorry, high here. So on that way, if we compare with the similarly the absorption and emission graph, there is a change in observance, there is a quenching in observance, and there is another thing I want to mention here. When you are adding particular some acceptor here, and after that you are exciting that particular system, so you are exciting only the donor, means where in earlier we are exciting the porphyrin, and here we are exciting only the perovskite. We are not exciting the acceptor, because you see if I excite here, the acceptor has no observance here. Okay, so as there is no observance, there is no emission, So once you are exciting with any pump light, so you are only exciting the peroxide. Okay. So once you excite the peroxide, definitely the electrons transfer only possible from peroxide to the acceptor. The opposite cannot be possible. Okay. And similarly, you can say that the 10 images, the sphere, the cubes, and here the plates. Also, this is not very clear one. And similarly, also we can understand about this, like how the electron transfer process has better in sphere, which is come from our pump probe technique. If you see, there is a this is the on-board one or the methylamine lead bromide one, the recovery, and in presence of testosterone anthony, there is a very fast recovery. Okay, and it is here also very fast recovery, but here it is almost same. Okay, means it makes sense that here in particularly in bigger like fused type of structure, they don't have that much strong interaction. That is because of the two type of interaction where we see the band gap changes. That means the change in the diving force, which is gives free energy, which is the responsible for the initiating the electron transfer. Okay, so this way we can explain whether you doped or whether you change the shapes, change the size or shapes, or you change the composition. Okay, so we play with all these things. Okay, and then we see how we can see how the charge combination happening. Okay, and we measure that. So on this, and there is another technique also here. It's actually not perovskite. This is another nanocrystal. If you see the pictures clearly, you can see here. So particularly these two pictures, if you see and compare here, so this is like, there is one type of shelling happen. Means you have a core nanoparticle. Okay, here if you see here, this is CIGS. This is like lithium, indium, gallium selenide, like that. The core nanoparticle, and then you are shelling, means you are covering with zinc selenide. Okay, so in that way, here also somehow we enhance the efficiency of the solar cell. And here I am showing the just of the tangent spectra. You can see this is for only CIGS, and here with the shelling, and with time interval you can see with how it is changes. The means only CIGS, it is a faster recovery rate, but in presence of zinc selenide, it is becoming longer time to recover. Okay, as you mentioned, like earlier, like we need very efficient electron transfer. Okay. Oh, we have few minutes now. Okay, so once we have efficient electron transfer, and then we can subtract it, and then we should have a very longer time interval to stay, the diffusion length point of view. So here we, in presence of scaling, we can see the better or I can say longer time recover electron incoming process. That way, which is a better use for solar cell application. Okay, so here also in the same way I can explain the last. This is the last one. So you can take your starting material inside here, and then you play with what type of electron transfer layer you are using, what type of hole transfer layer, electron transfer layer, and then you need a transparent substrate where you can pass the light, and then here. So we play with three different fluorine, like carbon 60, carbon 70, carbon 61, and this one it will depend upon how much the energy difference between this particular donor. And we saw here we have a better efficiency at carbon 60, it is like 9.2%, and we have a lower efficiency other two, even if the carbon 60 also it is better. Only the I think the ICBA, which is a different acceptor, which where we got the lower. And here we can see in kinetic stresses where the time recovery for the carbon 70 porphyrin is at much longer compared to other two. So that makes sense because it has more efficient, that means the combination taking more longer time. That means it is, that's why you have a more efficient or more efficiency when you make the device. Okay. And the electron transfer process also can be seen in IR, where you can see, once electron transfer happen, then definitely you have some cationic radical or anionic radical formation is there. So that also you can able to catch it in IR region if you go to there and you can measure that. Okay. So now we understand. So we need a very efficient charge transfer and efficiently charge separation, and also you can charge recombination. So these all the processes are the key parameter for the understanding how the solar cell happens, means performance of solar cell device we can see or you can improve. And also we observe like we need a long lead charge separation, means long lead charge separation means it should take for longer time. So then only you can see a better or more efficient solar cell. I think this one I can just share. I think my friend earlier speaker, Dr. Rao, and we have published 2 collaboration paper. It's long time ago, like 2010 and 2012. The similar here we have done some type of low dimensional material, and I did some optical studies. Okay, so other work I have done or what I presented, it is the collaboration from my previous research group in Coast or in Argonne National Lab in US, and here I was in Rajasthan, Central University Rajasthan, where I worked as assistant professor, and they were my supervisor. Okay, thank you. Okay, you can ask me questions now.
Okay. So by checking this perovskite-based solar cells, so how stable is this perovskites?
Yes.
What is the future of this perovskite-based solar cell?
I think last few years, I think the stability has improved a lot. Okay, so there is this 2 factor is what people are doing now. Let me open. So the stability point, like you are using lead as a toxic material. So now lead-free perovskite is started. And the stability point of view, it's really very good stable now. Earlier, it was not like you need your screen setting post. Maybe I can open it. And so now it will be like more stable because it has synthesized in the room temperature now. So okay, in synthesize maybe they have used the glow box, but slowly they started to. And once you have the filling ready, and what other measurement we have done, like all this pump-probe experiment we have done, it is done in room temperature, and it is stable, for longer time also. Even we play with so much laser power, like increase the laser power, and there is no change, means it is still stable. I think we have done similar study, like just putting the laser power for keeping for 3 days, 4 days, and we see if there is change in emission or something like that. So it's really stable. So the stability has improved a lot, but still work is going on to make it commercially available. I think that as you mentioned, like the PV Oxford, which they have, I think within this year they are going to sell the sales. So it has gone that far. Yes, the stability has improved a lot.
Okay, I think it's fine. Any students can ask something.
Thank you, sir. Now I request all participants to put their questions before the resource person for discussion.
I know this, it will be really little difficult for students to understand because, yes. But I think the most important thing is students should have an idea like how it is, the current research is going on. It's just not only the material science, you play with the material as Dr. Raut mentioned, the supercapacitor or lithium-ion battery. So it's like how useful what is the commercially in market available, and then you play with something extra because it's not like what is in available in market, we just work on that. Okay, so you have to do something extra and provide a better understanding to companies, like they can prepare little better device point of view. So that is the overall idea of doing some extra research on this particular system, whether it is a perovskite or any other material. I think yeah, it will be give little idea about what is happening.
Manoj,
Yes, sir.
hello.
Yes, sir. Yes, sir. I can hear you.
What is the thickness of 2D material?
Yes, yes. That it's depend like what type of use you are doing. But of course, definitely we are dealing with nanometer. So it is like 10 nanometer to like 50 nanometer. Even if it goes 100 nanometer. On that basis, you synthesize. Then once and then it's like when you put in application, we are not putting only the perovskite. Then also we are putting some extra like zinc oxide, some metal electrode, all this stuff. So when it is become a device, then it can become some millimeter thickness. But if you think taking about only the active material, which is your perovskite, it is in few nanometer range, in maybe 50 to 100 or 200 maximum. Yes.
How the efficiency varies with thickness?
Yes,
Whether it
yes,
is
yes.
varies
It's
or
not.
not?
Yes, yes, it is vary. It's not only the sample thickness. As I mentioned, the most important vary will be it's depend upon how much electron you are exciting, how much electron you are extracting from the surface. And we know even if you take a bulk material, you cannot excite the in between the crystal. You have to take from the surface, and the surface means it's only few nanometer thickness. So and that's the region here. So and the better will be the more it's like you have to optimize. It's not like less or more is better. Like it is like more or less we have to optimize like what thickness, and of course the structure, if there is properly contact, if the structure like all the cubes are properly aligned, or so in that way, if it is everything is perfectly aligned, and then all the thickness are appropriately arranged, and then maybe you have a better efficiency at the end. So it's almost it's depend upon the you play and you see how your efficiency is increased. So sometimes it's depend upon the thickness, definitely, and sometimes it's depend upon the everything. It's depend upon everything at the end. Like I mostly use with the lasers and do the experiments. And when we do laser experiment, we play with, okay, just make 10 type of spin coating, very simple way. Don't make 10, because if you make more, then the thickness will be little more, and then we cannot subtract light. Sorry, we can pass the light through the sample. Or there is, if the some other, like in IR region, some samples, then we make it like at least you make the surface very smooth. So in that way, we can reflect the light and we can see the absorption profile from the reflection light. So in measurement point of view, it will be like that. For device, again, we have to play. It's not necessary like thick or thin or something. So we can play and optimize, and at the end, we can see whether your efficiency is increased. So it happened in that way. Initially, people will get efficiency only 2%. Then suddenly, with minor change in thickness, it can improve also. So it is like that, yes.
Anyone interested in asking the question?
One question mark, please. Please, sir, give suggestion to our students for their future perspectives after
Okay.
graduation.
Yeah, I was talking to Ramesh sir about that, like, means, but maybe one more time, maybe we can discuss more detail. Maybe shortly I can tell, if the people, like students are interested in doing research, it's not necessary they should do research. They should do anything, but whatever they do, they have to, I think, do more, more focused attitude. So means, like, I'm telling in simple way, if students are interested doing banking or something, and I know people are doing for 5-year banking coaching, at the end also they are not getting, and some people are there doing 1-year coaching or without coaching also they are getting. So it's depend upon how focused you are. So this is one asset. The second asset, what we are doing, like, it's like, the, if you want to do research, I know the experimental research and then theoretical research. So theoretical research, you have to, of course, you have to understand the literature more clearly, means whether it is a solid state, whether it is a quantum mechanics. I think the theory they have to understand very nicely. And nowadays, it's not only like what you people are teaching. It's like everything available in internet. Look, students actually, what in 2000, when we are we are doing BSc, MSc, that time this type of facility was not there. Now it's everything available in internet. You want to listen lecture from MIT or Oxford, it is available. So I think, and then all the sources, it's not required to buy books. All the books also it is available. So I think this way, if they cannot just like what we are doing, just a mark basis, how we can get little extra mark or something, or how to get little more practical mark or something. So that will not actually help particularly here, because in practical point of view, if you see how many students they are playing with the diode and triode, that if one triode is not working, students should remove this thing and they can fix that. It's not, as I think maybe Ramesh sir knows, when Dr. Raut was in +2, that time Chandrasekhar Raut, he able to fix the TV. He's able to fix tape record. Means that time he was, we have a friend who was doing diploma in this. Then he just learned little bit from him, and then that time nothing was there, but still he can manage with play with the TV. He can manage with play with the, he can change the circuits, he can change the everything. He was doing that, and that experimental hand helped him. I think when he entered to Genshare, I think he has done, means he has a very technical hand now. So that's why those, even if the sweat fuel cell, these things are not that much required technique. So both way, whether you are doing theoretical research or experimental research, like, we have to do, means, more focus. Our attitude should be more on to understanding the physics, the understanding the experimental things, how it is happening. It's not like just, I know maybe nowadays the exam pattern is changed. Our time we have to just write 5 questions and just paragraphs. You just now I think it is more technically questions, maybe like more like exam oriented, like short questions, maybe like problematic. That will also improve the understanding of the subject. Earlier, like, we have to just write 2 pages about one derivation, then it will be sufficient for that. So it's not, so that's right. So, and once, and then later on, if they want to carry the research, then they have to do the master degree in, they should try giving exam like JAM and other things, where they can go to the IIT or NIT to doing master degree. Means if you do master degree in a very good institute, then only you have very good research facilities there, and then only you can learn little more. And it is very simple. You have to just prepare. When the third year students, if they want to go for master's degree, they should not go for colleges like Rebensha or other things. I know they getting there also difficult. But if you prepare little well, like you have to see how the jams or other exams, how the question pattern is coming. The technique is simple. You just take last 5-year questions or 10-year questions, and you try to solve it by yourself. Now answers also available. You see how the problems are coming, and on that basis you can prepare that way, and you give the exam there. And once you enter a very good institute, I like NIT, Raulkela in Odisha, all other NIT, or that is, even if the place where Chandrasekhar Rao is working now, that place also they started MSc, but I think that is they are like paid MSc. They are taking little more money. Other things, other like NIT, other things, there is cheap. Means it's just admission. What we have done in BSc. So similarly, if they can do a very good master degree, and then it will be easy for them, because in there, like 1 year teaching, 1 year or 6 months, they have to do the research work. And they have to do research work with research scholar and with the senior researcher, which means you will get a very good understanding and very good experimental hand also. So once you enter there, and then it will be easy. Even if it's okay if you do MSc some other place, and then later on what we did, when I went to IIT Madras that time also, let me clear this way. Like in IIT Madras, when I entered, I thought, okay, it's very nice, because all the ledgers are there, experiments are there. But then when I went to US, there it's nothing. I mean, in that time, it's like IIT Madras also looks like very small. Means and we don't are following the safety protocol, when we don't have that much experiments like that. So it's better if you go for higher study in better institutes, if you can try. And for trying that, it's really easy. I don't think you need much, because people are not putting effort. Like if my home in Odisha, I'll try, okay, somewhere in Odisha I'll get it or something like that. So so once you enter in a good institute, you have more exposure, you have more understanding how the system working, and then it will be more easy for students, really easy. And nowadays, even as internet is more open, everybody has mobile and everybody can see how, so I think it will be easy for students nowadays. Of course, the competition is really high every time. So yeah, that is the thing. If you want to do research in experimental, then today onwards you go to the theory class and the practical class equally. And practical class, whatever instrument is there, you play with that. Don't just finish reading science go. I think you just destroy the instrument and again repair that and fix it. Even if you cannot fix it one, I feel like that's okay, because college can buy another one. But still, I think students should play with that, whatever they have, and they should understand. And you open the YouTube there, you see YouTube how people are doing, and then you can do that. And more importantly, you have to understand like how the particular component works, how this means you can complete that, and of course the physical significance. So yes, and how
understanding the topic is important. Don't
yes,
just
exactly.
remember and write in exam for marks. Marks is not very important, no? Because if you remember and write in exam and get marks, and you cannot qualify some entrance, then it's no.
Yes, exactly.
If you get
So
less mark, also fine, but try to understand the basics. What is the principle? How it works? It should be explained to others, and you have to think. Your thinking power should be improved, so that you can answer all these questions or mathematical questions. That kind of power you should have. So you have to think the basics. Actually, you should understand that. And one more thing I want to tell, after BSc also there are many places like ISERS, NISERS. So they have some entrance and they take students for integrated PhD. And if you
Yes,
want to
yes.
do research,
Means directly it will be MSc plus PhD. Yes.
yeah, so there they also give fellowships. For monthly fellowship also they give. And you can directly apply for them. NISERS, in Bhubaneswar one NISER is there. Similarly, ISER. Many states have ISERs now. So in Berhampur, one ISER is there. So like that, those places you can apply. After your BSc also, you can apply. In BSc third year students, they can appear that entrance. And they give fellowship also. So many options are there in a research line if you want to go in a research. Otherwise, there are other lines also. You can decide what you want to do depending on your interest. That is more important. Okay. Okay, sir.
Even if Central University is also good. In Odisha, I think that new one, they don't have physics department now. But the other central universities where I was a faculty, like in Central University Rajasthan, that is also just new university, like it started 8, 9 years ago, 2011. Yeah. So in that also, within 2-3 years, they developed the infrastructure very nicely. It means all the means research wise not, but for master degree it is really good. So they conduct some CUCT exam, all the central universities also. So they are also, and of course nowadays you can apply always some fellowship also, like Inspire fellowship. For MSc also they are providing some fellowships. That is also there, but that you can try later. Yes.
Thank you, sir.
Thank you, sir. Now, I would like to invite Dr. Ramesh Kumar, sir. Please, sir. Thank you, sir, for your kind and informative informations. Now, I would like to invite our HOD, Dr. Ramesh Kumar Sahu, sir, to present his views.
Thank you, Manas and Chandrasekhar, for your kind cooperation for the department and for your nice presentation, excellent presentation. I again thank to both of my old students, Chandrasekhar and Manas. One question, Chandrasekhar, your interaction, what potential you take?
Sorry, sir, I didn't get it.
ମୁଁ କହିଲି ଆମର ଯୋଉ ନାନୋ ପାର୍ଟିକୁଲର ଇଣ୍ଟରାକ୍ସନ ହଉଛି ଆମେ କୋଉ କୋଉଭଳିଆ ପୋଟେନସିଆଲ କୁ ନଉଛୁ ଆମେ ପାର୍ଟିକୁଲ ଫିଜିକ୍ସରେ ନଉଛୁ ଯେମିତି ପୋଟେନସିଆଲ ସେଥିରେ ପୋଟେନସିଆଲ କଣ ଚେଞ୍ଜ ହଉଛି ନା କଣ ନଉଛୁ ଆମେ
ପୋଟେନସିଆଲ ମାନେ ପୋଟେନସିଆଲ ଏନର୍ଜି କହୁଛନ୍ତି
ହଁ ପୋଟେନସିଆଲ ଏନର୍ଜି ଇଣ୍ଟରାକ୍ସନ ପାଇଁ ତ ପୋଟେନସିଆଲ ଏନର୍ଜି ଦରକାର
ହଁ interaction like suppose 2D materials we have van der Waals interaction between the layers. So there is a gap between them. So they are not bonded. All these 2D material layers, they are not bonded like chemical forces. So they have some van der Waals force between them. So they are not directly bonded. So these atoms are chemically not bonded. They are like van der Waals force are acting between them. So that's why people are using to separate these layers. So these separates you can do by some exfoliation or micromechanical exfoliation. So by that you can, that's why this weak interaction is there between these layers of this 2D material, so that you can remove it. And if you are telling about interaction between some other nanoparticles or nanostructures, so it is possible to make positive charge materials or negative charge materials. So that is also possible. Suppose if you want to modify some neutral charge inactive material, you can make it positive also. So if you can modify this material with some other material, so they can be positively charged, and also some materials can be negatively charged. So like one example, graphene. So you can make it positive and negative also. If you can make both the charges, so they can directly like there will be attractive force between them. So this so it is possible actually. There are different types of interaction between different types of nanostructures or nanoparticles. So depending on that, we can achieve that. Yes, sir.
Okay. So very thanks to both you. You cooperate to the department at any moment we need.
Now, how many students are there in batch now?
24.
So 24 is the seat.
In third year science.
Third year. So all in 24 physics, chemistry, math, all are 24.
Physics 24, chemistry 24, math 16.
Math 16. Rama sir is not there?
No. Rama sir now at Kendapada College, and he is controller of examination at Kendapada College.
Okay. We thought where is he now? We didn't know.
Very soon he will be retired.
Okay.
March 22 रे से retired करिवे.
Oh, March 22. Okay. ଏବେ କଲେଜ ଖୋଲିଗଲାନି?
କଲେଜ ଖୋଲିଲାନି ମାନେ ଅନଲାଇନ କ୍ଲାସ ହଉଛି ଆଉ। ହଉ ସାର୍, ଭଲ ତ ଅଛ ଆଉ କଣ? ଭଲ ଠାକୁରଙ୍କୁ ମଧ୍ୟ ପ୍ରାର୍ଥନା କରୁଛି ତମେ ଆହୁରି ଆଗକୁ ଯାଅ ଏବଂ କଲେଜ ଡିପାର୍ଟମେଣ୍ଟ ସମସ୍ତଙ୍କ ନାଁ ରହୁ ଏବଂ ଆମ ପିଲାମାନେ ଯୋଉ ମୋଟିଭେଟେଡ ହେଲେ ମୁଁ ଭାବୁଛି ପିଲା କିଛି ତା ଦେହରୁ ଲର୍ନ କରିଥିବେ। ଅନ୍ତରାମ ସାର୍ ଶୁଣୁଥିଲେ? ହ୍ୟାଲୋ। ଅନ୍ତରାମ ସାର୍ ଶୁଣୁଥିଲେ, ଶୁଣିକି ମତେ ଭାରି ପ୍ରଶଂସା କଲେ ଏବଂ କହିଲେ ପିଲାମାନଙ୍କୁ କହିଦବ ମୋ ପକ୍ଷରୁ, କାହିଁକିନା ସିଏ ଇଏ ଲିଙ୍କରେ ଜଏନ୍ କରିପାରିଲେନି, ଜୁମ୍ ଲିଙ୍କରେ ନେଟ୍ ପ୍ରୋବ୍ଲେମ ଏମିତି ହେଲା, ଜଏନ୍ କରି ୟୁଟ୍ୟୁବରେ ଶୁଣୁଥିଲେ। ଆସିଲେ ଦେଖା ହବ, ଡିପାର୍ଟମେଣ୍ଟକୁ ଦେଖିବ ଆଉ। ତମେ ଗଲେ ତମ ପଛରେ ପିଲା ଯିବେ ନା ଆଉ, ସେଇଟା ହଉଛି ତ ଆମର ସୌଭାଗ୍ୟ ନା।
ସାର୍ ସେଇ ଛୋଟ ଛୋଟ ଏକ୍ସପେରିମେଣ୍ଟ ମାନେ କିଛି ନୂଆ ଆଣିବାକୁ ଚେଷ୍ଟା କର ଯେ ଯେମିତି
ସେ ତ ବର୍ତ୍ତମାନ ଏଇ ଯୋଉ ସିବିସିଏସ୍ ସିଷ୍ଟମ ହେଲା, ଲାବରେ ବର୍ତ୍ତମାନ ଇନଷ୍ଟ୍ରୁମେଣ୍ଟ କିଛି ନାହିଁ କହିଲେ ଚଳିବ। ଆମେ 24 ଜଣ ପିଲାରେ 2-3ଟା ଏକ୍ସପେରିମେଣ୍ଟରେ ଗୋଟେ ଲେଖା ସେମିଷ୍ଟାର ସାରୁ। ଖାଲି ଆମର ପ୍ରୋବ୍ଲେମ ନୁହଁ, ଏଟା ଆମର ରେଭେନ୍ସାରେ ବି ପ୍ରୋବ୍ଲେମ। ରେଭେନ୍ସାର ଯୋଉ ପିଜି ର ଯାହା ଥିଲା ଏକ୍ସପେରିମେଣ୍ଟ, ସେଗୁଡା ବର୍ତ୍ତମାନ ୟୁଜରେ ବସିଗଲା। ତାଙ୍କର ପିଜିରେ କିଛି ଏକ୍ସପେରିମେଣ୍ଟ ହଉନି। ତାଙ୍କର ହେଡ୍ ଯିଏ ପ୍ରଫେସର ଆସିଥିଲେ ଯାହା କହିବା କଥା, ତାଙ୍କର ପିଜିରେ ମଧ୍ୟ କିଛି ଏକ୍ସପେରିମେଣ୍ଟ ହଉନି। ଏଇଟା ହଉଛି ଓଡିଶାର ସିଷ୍ଟମ ଆଉ। ଏକ୍ସପେରିମେଣ୍ଟର ପୁରା ବିଲୋ ଷ୍ଟାଣ୍ଡାର୍ଡ କହିଲେ ଚଳିବ। ସେଇଟାର ଯେପର୍ଯ୍ୟନ୍ତ ଡେଭଲପମେଣ୍ଟ ହେଇନାହିଁ, ଯେ କୌଣସି ଡେଭଲପମେଣ୍ଟ ହେଇପାରିବ ନାହିଁ। କଟିଗଲା କି?
ନା ଶୁଭୁଛି ସାର୍, ଶୁଭୁଛି। ଛୋଟ ଛୋଟ ଟେବୁଲ ଟପ୍ ଏକ୍ସପେରିମେଣ୍ଟ ଗୁଡା ଯୋଉ ରାଜସ୍ଥାନ ଆମେ ଥିଲାବେଳେ ଆମେ କିଣିଲୁ ପିଲା ପାଇଁ, ସେଗୁଡା ସବୁ ମାନେ ବହୁତ ଶସ୍ତାରେ ବି ମିଳିଯାଉଛି। ମାନେ ଏମିତି ଅଛି ଯୋଉଟା କି ବହୁତ ଶସ୍ତାରେ କିଛି କଲେଜ ଯଦି ତାଙ୍କ ପଟେ ଲାଗି, ଯେମିତି ସିଙ୍ଗଲ ସିଟ୍ ଏକ୍ସପେରିମେଣ୍ଟ ଗୋଟେ ହେଲା, ସିଙ୍ଗଲ ସିଟ୍ ଏକ୍ସପେରିମେଣ୍ଟ ହେଲା, ଗୋଟେ ପଏଣ୍ଟ ଛୋଟ ଲେଜର ଆଉ ଗୋଟେ ଖାଲି ପିନ୍ ଆମର ଦରକାର, ଏଇଟା ହେଲା ଗୋଟେ ସ୍କ୍ରିନ୍ ଦରକାର। ମାନେ ସେଇ ଟାଇପର ଏକ୍ସପେରିମେଣ୍ଟ ବି ପ୍ଲାନ୍ କରିହବ, ଯୋଉଟା କି ବହୁତ କମ ପଇସାରେ ବି ଆରାମସେ ଡିପାର୍ଟମେଣ୍ଟରେ ଆଣି ହବ। ମାନେ ଖାଲି ଗୋଟେ ଟୁଲ ପକେଇଦେଲେ, ଗୋଟେ ସ୍କେଲ ପକେଇଦେଲେ ଯୋଉଟା ଆମର ଇଏ, ଆଉ ଗୋଟେ ଖାଲି ଭିତରେ ଗୋଟେ ଲେଜର, ଛୋଟ ପିନ୍ ଲେଜର ଗୋଟେ ଲଗେଇଦେଲେ, ମଝିରେ ଗୋଟେ ପିନ୍ ଲଗେଇ ଦେଇ ଗୋଟେ ସ୍କ୍ରିନ୍ ଆମର ଥୋଇଦେଲେ। ସ୍କ୍ରିନ୍ଟା ଆମର ପିଷ୍ଟ ବୋର୍ଡ ଟାଇପର। ତାପରେ ତାର ଆମର ଡିଷ୍ଟାନ୍ସ ମୁଭ୍ କରିକି ପାଟର୍ନ ଡିଫାକ୍ସନ ପାଟର୍ନ ଦେଖିକି
ଆନାଲିସିସ୍ କରିବ ଆଉ। ସେଗୁଡା କଲେ ହବ, ସେଗୁଡା କୋର୍ସରେ ରଖି ସେଇ ଟାଇପର ସେମାନେ ରିଲେଟେଡ କରିବା କଥା। ଯାହା ଡେଭଲପମେଣ୍ଟ ହଉଛି ସେୟାକୁ ଆଖି ଆଗରେ କୋର୍ସରେ ରଖନ୍ତେ, ताले पिला गुडा बेनिफिटेड होते पिला गुडा भी मोटिवेटेड होते होते रिसर्च माने एक्सपेरिमेंटल फिजिक्स रे भी बहुत जिंस अछि
एटा इंटरेस्ट आसंता कारण आमे मन कर ओटा जिंस पढिले से जिनसटा यदि आमे देखि पारिले ताहले जाई से इंटरेस्ट माने से पाठ में मजा आउत नहले खाली जेते भी पढ़ी गले किंतु पिला भी एठी जानि पारिए पिला एठी एक्चुअली जो माने जो जिनसटा हमने भलो बुझिबा को चेष्टा करचंदी सेटार इवन सिना कॉलेज रे नाही किंतु इंटरनेट रे अछि तो सेटा से माने इंटरनेट रे एटलीस्ट एक्सपेरिमेंटल से देखि पारिबे कि ओके ये एक्सपेरिमेंट रे एई टाइप रो एक्सपेरिमेंट होउची से फोटोइलेक्ट्रिक इफेक्ट हो जे कौन सी इफेक्ट जो जे कौन सी जिनस आमे स्टडी करूचे पढुचे इवन न्यूक्लियर फिजिक्स एक्सपेरिमेंट उडा भी सब माने सेउडा तो
सेउडा नेट रे बाहर कर देख पारे
सेटा भी भला होता सेटा
यूजीसी किछ दउथिबो कि दउ
ना ना यूजीसी रो फंडिंग वर्तमान पूरा बंद
हां हां से माने
2012 रो फंडिंग पूरा बंद 2014 रो फंडिंग बंद से यूजीसी फंडिंग हेले ना के पंत एक्रेडिटेड हेई नै ना एक्रेडिटेड हेले रुसा ग्रांट यूजीसी ग्रांट पाइले ताले किछि डेवलपमेंट
सेटा हेई पारिबो फंड मिलले हेई पारिबो
ओ मानस
हां सर थैंक यू सर
now I request Deepika to give vote of thanks.
A very good afternoon to all. As all good things come to an end in life, so is the webinar. On behalf of Physics Department, I like this opportunity. I take this opportunity to propose vote of thanks to those who have directly and indirectly contributed this webinar on advanced two-dimensional material for energy application organized by our department. At the outset, I thank our resource persons, Professor Chandrasekhar Raut sir and Dr. Manas Ranjan Parida sir. We all are really enlightened with your knowledge and presence. We are thankful to our Honorable Principal sir for his enthusiastic support and our beloved HOD, organizing committee and staff for their unflinching support and coordination. My heartfelt thanks to the students who have active participation. With these warm words and a kind message, we move to the end of today's webinar. Thank you to all.
Thank you sir.
Thank you.
Thank you all. Now, thank you all. Now the seminar is closed. Manas mu tama se pore katha habi
हां सर थैंक यू सर थैंक यू
सर मु रहिली परे कथा
हां सर ओके थैंक यू सर